Good morning, Astronomy 1020. Welcome back. Today is our second lecture, which I call Lecture 1, and we're going to be learning all kinds of useful stuff today. Let's start off by seeing who's got their Casio FX260 solar calculators. Show them up. Let's see what you got here. Yeah. All right. I'm very proud of you guys. Walter, you got yours? Oh, hey, Walt, I think I see an unsanctioned calculator. Walter, what are you rocking there? What's going on? Okay, Walter, we're going to have a talk. Or there you are. Okay. Now, if you insist on using that calculator, you can do it. But we're going to run into some troubles along the way, okay? And that's because with so many people, I'm going to be teaching you guys some weird, nutty stuff. And it's going to get confusing if everyone has a different calculator. So usually when you bust out a piece like that, it means you've had some background in math. Do you, what math have you had? Like, have you done calculus or have you done algebra? Where are you at?
I have done pre-calculus and now I'm taking applied calculus.
Okay, so this man's got some math chops. And that sounds like probably if I asked you to take a fourth root, you'd know how to do that on your calculator, right?
Yeah.
Well, that's cool. So in that case, this could probably work out for you. And I can't prevent you from using an unsanctioned calculator as much as I would like to. I'd like to come to your house right now and throw that thing in the trash and say, you use this calculator, but I can't do that to you because that's illegal. They won't let me do that. But the instructions are going to go a lot smoother for everyone, especially those without a lot of math background, if we all have the same piece here. Another thing, Walter, that my friends who've taken this class who do have like physics and math and engineering backgrounds, they've learned something kind of special by learning to use this calculator. Is that
you're on it right now?
Yeah, I'm on it right now. How about you? Someone might want to mute themselves. Okay. One of the cool things about this calculator is even if you do have some math chops, you realize how awesome it is to have a little pea shooter at your side. This is kind of like the equivalent of a 6-shooter, right? And what you've got there, Walter, is a calculator bazooka, okay? And there are times where we need a bazooka when we have to blow up the whole enemy base, but sometimes we just want to John Wayne and pull it out and, like fire off some math. So don't underestimate the power of a little pea shooter like this to get the job done cleanly and simply. I want to teach you to love this calculator so that when you go on to study engineering or mathematics, you will spread the love, okay? So here, consider it. That's all I'm saying. The rest of you, thank you for buying this. If you do not have this calculator, you're doing it wrong. You're starting off bad, okay? I got stuff to teach you. That's why you pay me. And I can't teach you unless you have the tools. So you'll have to make do if you don't have it today somehow. Let's start off and think about where we left off last time. Last time I taught you guys about scientific notation. That's really all we had time for. And I'm hoping that you guys still feel okay about that. There'll be some opportunities to try it today. Let's do a little quick test here. Suppose I put a funny number up on the board, like 1, 2, 3, 4, 5. 0.6789. Suppose I picked a random person like Mia. Mia, you're the first square in my square. How would I put that in a scientific notation, Mia? Show me what you've learned.
You need to take the index number, which would be 1.
The lead digit, yep.
And then you would move the digit, the decimal over up until before the index number.
Okay. What I call the
and then
lead
that
digit.
amount of spaces that you use would be the exponent. Or
I like it when you say that. All right, so now tell me what to write. It sounds so nice when you say it like that, but tell me what the answer is.
Sorry. So it's going to be 1.2345
I guess everything
times
now, right?
10 to the 4th power.
Very good, because you've moved 1, 2, 3, 4. 10 to the 4 is an order of magnitude of 10,000. I like your chops, Mia. You've done right. You've proven that you can master this. Okay. Scientific notation is something that eventually will be very easy because we'll just use it all the time. So if you're still feeling shaky about it, hang onto your hats. You'll get plenty of exercise, okay? Today we're going to learn a few vocabulary terms. We're going to learn how to talk about angles. I'm going to teach you about scale models, and I'm going to teach you about scientific notation. Before we launch right into it, let me remind the class that you can follow along at home. Where's my Blackboard page here? Remember that in the Blackboard page on the left, PowerPoint slides are here if you ever want to download them. And I have lecture notes, which are crummy little Roman numeral lecture notes that you can follow along with. Last class we did, I hate how it makes you download that. That's ugly. Let me go to my folder here and see if I have those. So I'm not downloading stuff I already have. Last class you had your introduction to astronomy 1020, and we sort of covered these topics. And today we're going into lecture 1, and we'll be covering some of these topics today. Notice that I have a diagram and one of the formulas you're going to learn. This is just some handy stuff to have around. I still think you should take notes. I think that's really good for you to take the notes that I'm writing down, especially because people don't always read the book in its entirety. So follow along as best you can. We're going to start today, how should we do this? With Earth's orbit, okay? And one of the reasons we're going to start by talking about the orbit of Earth is the motion of Earth, both its rotation and its orbit, affects how stars move through the nighttime sky. And in the first few weeks, we're going to be trying to understand how stars rotate across our sky, how to keep track of them, and how to think intelligently about these things. So let's start by showing you guys a couple of pictures here. Oops, sorry, you're not looking at my screen. Just a moment, guys. Okay, so let me share that screen again. And here we go, function F5. Did I show this to you last time? What is it?
It's Orion.
Mm-hmm. Exactly. Is Orion up every night?
No.
No. Do you remember what time of year you can see Orion?
Isn't it this time of year?
Yeah, in the winter. Especially like late autumn, Orion starts poking its head up late in the evening. And then as we drift through the new year into spring, you start seeing it earlier and earlier in the night. And eventually, by the end of this class, Orion won't be visible in your sky anymore. You'll have to wait till next winter. Today, one of the things we're going to be doing is we're going to be calculating the diameter of this legendary star known as Betelgeuse. Never forget Betelgeuse. It's the bright red shoulder of Orion, and it's one of the coolest stars in the nighttime sky for a couple of reasons. We'll get to that eventually. To understand how Orion works its way through the sky, you'll need to know a few things about Earth's orbit. And I've got a few things to show you here. Let's imagine that we're kind of looking down from the North Pole in space. I'll define that in just a moment. And if you could look from above the Earth, if you could fly out from the Earth in your Millennium Falcon and look back down, you would notice that during the course of the year, Earth orbits around the sun in a counterclockwise direction, and it's also spinning on its axis simultaneously in a counterclockwise direction. It turns out that most things in our solar system have a sort of counterclockwise spin to them, and that's going to be quite important. So from time to time, it might be helpful for me to show you guys a little globe here. Here you've got Earth. Its daily motion is its axis spin. Notice that I'm taking pains to spin counterclockwise as seen from above. Hopefully the orientation of this camera doesn't screw that up, but you always want to make sure that if you're looking at the United States, you're rotating so that Rhode Island is first and California is trailing it, okay? That's how you want the spin to go. Let's take a couple of notes about this. Let's start with Earth's orbit. Okay, so first thing is that Earth has an axis spin. And the axis spin gives rise to the day. And as you guys know, one day is equal to 24 hours. I'm guessing that I'm not blowing any minds here with that. That's something that you should know. But I want you to write it down anyways, because I want you to notice the format in which we're doing things here. This is your first of many conversion factors. Conversion factors play a huge role in all branches of science, but especially in astronomy. So make a note that this is called a conversion factor. A conversion factor relates one set of units, like days, with another set of units, like hours. Sometimes the conversion factors will be familiar to you. Most of you know there's 24 hours in a day. But many of the conversion factors that I teach you will be weird, unfamiliar things, like the number of joules in an electron volt, or I could get scarier if I wanted to, but we'll leave it there for now. Every time I write down a conversion factor, you should write it down and try to follow my notation for the units, okay? So there's Earth's axis spin, that gives rise to the day. And then there's Earth's orbital period. That's its yearly motion around the sun. And that gives rise to 1 year, which is approximately 365 days. Actually, Philemon in my 1010 class is going to learn that there's 2 types of year. There's a sidereal year and a tropical year. I don't know if I want to get into those nuances just yet, but one of them is 365.25 days and the other is 365.24 days. For now, I'm just giving you 3 digits because that should be good enough for our everyday work here. As mentioned a moment ago, as Earth orbits the sun and as Earth spins on its axis, it's spinning counterclockwise, which turns out to be a really important point. We can use this to define directions in space, all right? So if you're standing on Earth, from now on, anything in the direction of Earth's north pole shall be considered northward in space. Anything in the direction of Earth's south pole, that'll be considered southward in space. Now, east and west seems weird at first. For instance, check out my globe here. You see familiar old America staring back at you. We've got the East Coast here, where we are in Rhode Island. We have the West Coast there. So it kind of looks right now like east is in that direction, right? Of course, if I spin 12 hours into the night, now America is facing me, and east seems to be pointing in the other direction. So it seems like east and west would get messed up in space until you give it a harder think. You think a little more carefully about it, and you think, what if east was a direction that was related to spin? What if we defined eastward? Notice that as I rotate America here, I'm always rotating in an eastward direction. What if counterclockwise was east? That would be a weird thought that the more you think it would make very good sense. So maybe that wouldn't have come natural to you. That's why I'm here to help, okay? From now on, we will define counterclockwise and I'm going to use a triple equals here. Triple equals means it is defined as such. Don't argue with me, okay? Counterclockwise is equal to east. And of course, that will suggest that clockwise is west in space. And by the way, that holds true if you are standing out at the nighttime sky and you're watching stars rotate. Stars rise in the east and set in the west. I want to be careful here. It depends whether you're looking north or south. You want to keep this from getting confused, but in general, the diurnal motion of the sun rises in the east and it sets in the west, but you're still defining east as counterclockwise, provided you're looking south. Maybe I should just leave that one alone. But we're going to learn about how the sky rotates in good course, okay? Okay, so as Earth makes its journey around the sun, it's traveling along a path, which I am going to define in a moment as the ecliptic. But just for a moment, I want you guys to take a look, excuse me here, as I share screen. Take a look at my slides again, and let's take a peek at slide 15. I want to introduce a couple of vocabulary terms to you. I'm going to define the path of Earth in just a moment as the ecliptic. And I'm showing you here the ecliptic as a blue circle. It looks to your eyes like the orbit of Earth is a perfect circle. And I got to tell you, it's damn close to one. It's almost perfect, but it's not quite. That means there is a point in Earth's orbit, which we call perihelion, where the Earth is a little bit closer to the sun. And there's another point called aphelion, where Earth is a little bit farther from the sun. These are important vocabulary terms that I would like to use with you. So we're going to write those two things down, okay? So in Earth's orbit, we have a position called perihelion. That's the point in orbit closest to the sun. And then we have another vocabulary term called aphelion. And that's the point farthest from the sun. Take a moment to copy that down while I adjust the glare.
Professor.
Hopefully that helped a little bit. I'm going to try to make sure, when I'm writing stuff down, I can go kind of quickly sometimes. I want to make sure you guys, all of you have time to write this down. So Mia, how you doing? Are you done? Does anyone need another second here? All right. I'm going to erase. Oh, hello?
I'm all done. You can erase.
Okay.
Sabrina.
Oh, hi, Sabrina. Nice to hear from you.
Hi.
Okay, I'm going to erase this. I'll try to keep asking this because sometimes I go too fast for folks. All right. If Earth has a closest approach and a farthest approach from the sun, it's going to turn out to be useful for us to define the average distance between Earth and the sun. But before we kind of get into distances, let's just talk a little bit about distance and especially about metric units, which we're going to be using in this class. So let's talk about some metric units of distance. If you guys were present for lab, and I hope you were, otherwise, by the way, I hope you guys have all turned in your lab 1. I have to address this question because people keep asking me about it. I grade papers on Sunday. I'll be grading lab 1 on Sunday. I'll be grading the homework that we do today, homework 1 on Sunday. Once I've graded it, at the end of Sunday, the submissions are cut off. So I do not allow, I allow submissions up to Saturday or Sunday morning, but homework 1 and lab 1 cannot be submitted after Sunday. So please get those in. I don't really have to worry about you guys because you're here attending the live show and you're probably going to submit the moment we're done. So ironically, you guys are the least important people to tell this to. But for anyone else out there watching this video later, Sunday's the cutoff. So don't screw this up. Okay. If you were present for lab, you guys will remember that I used a meter stick, one of these meter sticks to measure my height. The average height of a human is just under 2 meters tall. Okay. So a meter goes from my shoe up to my belt, roughly. That's the length of a meter. It's kind of like a yard, but better. And the meter is the golden standard for units of distance in science. And we can subdivide them into other metric units as well. And I just wanted to familiarize you with that. All right. So we have the meter. And we abbreviate the meter 1 lowercase m. The meter can be broken down into units called centimeters, which you can see here. I like to think of a centimeter as roughly the width of my pinky fingernail. I'm always trying to come up with analogies so I can measure stuff in my mind. A centimeter is about the width of your pinky fingernail, okay? And a meter contains 100 centimeters. There's a conversion factor for you. Remember that you can subdivide centimeters into these. Let's see if this shows up in the video. I might have to adjust my focus. These tiny little tick marks. Okay. At certain times during the class, I might want to zoom in. So I need to open up my Logitech control panel. That way I can manually adjust the zoom. Bear with me, guys. This is cooler when we can kind of interact in lab because I can kind of get up in your face and you can hold these things in your hand. Since this is all being done, let's see if I can adjust my focus to like 36. Okay. So here we go. So there you can see a centimeter. Notice it's about the width of my pinky fingernail. The little subdivisions you see there, those are millimeters, okay? And you can count yourself. There are 10 millimeters in 1 centimeter. A millimeter is a tool appropriate for measuring the length of an ant. That's what I think of it silly like that. Okay, so let's take that down too. So we have 1 centimeter contains 10 millimeters. We'll often use centimeters and millimeters in our laboratory, which is why I should introduce them now. 1 meter contains 1,000 millimeters, if you want to include that too. When we measure distances across the surface of Earth, meters are, of course, too clumsy a unit to use. Then we want to bust out the kilometer. Last time I gave you guys a bunch of metric prefixes. How many zeros are represented by a kilo? Use your cheat sheet if you have to.
It wasn't 12, right?
3.
No, that's trillion and that's terabyte.
Oh.
Tera.
Is it 3?
It's 3. Correct. That's okay. We're learning this stuff. So I'm going to constantly, when I ask you guys questions, it's to help with memorization. Okay. So play along with me as you guys have been willing to do. So appropriate for measuring the radius of a planet or sometimes even a star, we'd want to use the kilometer. 1 kilometer is equal to 1,000 meters. As both Mateus and Andrew will be able to tell you, because they've taken my solar system course, this happens to be a conversion factor that we use all the time. Isn't that right, Mateus? This just comes up all the time. So I'm going to ask you guys to put a little star next to it. Yes, Brian. Oh, I didn't know if someone called out at me, but that's cool. But yes, I was getting some backup from Mateus here and just saying, trust me, you want to put a little star next to this because you're going to use this all the time. Eventually, I won't need to write this down for you because you'll just accidentally memorize it. But for now, we're introducing you all slow. Okay, now that I've done some metric units of distance, we're ready to talk about measuring solar system size distances because we want to start getting out into deep space and thinking about stars and galaxies and fun stuff like that. If you were going to poke around the solar system, which we're going to do, kilometers are much too clumsy a unit to measure. Notice that it's hundreds of millions of kilometers between the Earth and the Sun. It becomes useful to define a new unit of distance for astronomy purposes known as the astronomical unit, or 1 AU. It represents the average distance between Earth and the Sun, and it has a value of 150 million kilometers. Let's write that down. Introducing the astronomical unit, otherwise known as 1 AU. 1 AU is the average distance between Earth and the Sun.
No, what?
Uh-oh. Can you guys read that? Average distance between Earth and Sun. One AU has a value of 150 million kilometers. Ding, ding, ding. I think I remember that there was a rule in this class. Hadn't we decided that we had a rule? Something about numbers? Who knows the rule? Cheyenne, do you know what I'm talking about?
I know what you're talking about. It's can't get the words out. After I think a million,
Yeah.
you use it to a scientific notion.
Yes. Beautiful. Beautiful. Good job. After one, when the number gets over, and we have a number that's bigger than a million, don't we, Cheyenne?
Yes.
That sounds like a you job to me. That sounds like I'm going to need you to help me put this into scientific notation. You want to give it a whack?
Yeah, give me 1 second.
Sure. I need to get my little stool here, so that's cool. Okay, deep breath. Let's give it a shot. Actually, I'm going to erase. Can I erase this? I want to start at the top. One AU, 150 million kilometers. Okay, Cheyenne, help me do this.
I'm just double checking because I remember last class I was having difficulties rounding, so I was going back to the notes to make sure.
You don't need this number.
Or I don't need to round.
Cheyenne, this number has been pre-rounded for you. So let's take that off the table. Why don't you just start by thinking about the lead digit? What's your lead digit?
It's 1.
All right, so we'll start there. Anytime you start to choke on scientific notation, just think, what's my lead digit? And that's how you begin. All right, so we'll write this again, 1 AU. All right, so what should I do after the 1?
You move your decimal to there, so it'll be 1.5.
Good. And then what?
Times
Times
10, I believe it's
And how many times do you have to move that decimal?
8 times.
Very good. Because it's 1, 2, 3, 4, 5, 6, 7, and we're moving it over the 5 as well. So it's 1.5 times 10 to the 8, and then we always keep our units kilometers. Now, Cheyenne, you've done great, and this is what is called proper form of scientific notation. It's proper form to have a single lead digit between 1 and 9, followed by a decimal point and some change. That's where the rounding comes in. And then your power of 10. Your textbooks, at the back of the book, they have a number of conversion factors. When I used to teach this class in person, and when we hung out together in person, it'd be very helpful for students to sometimes use the back of the book where they have useful conversion factors. Notice they put the 1AU right at the top here, and it's hard to see because it's fuzzy, but they put it in proper form. They have 1.498 times 10 to the 8 or something, but whatever. We can just use 1.5. Sometimes, Cheyenne and friends, it's nice to be improper and to do things, you know, just a little weird. That's how I like to do things. So even though, oh, by the way, why don't we all punch this into our calculators, right? To punch into our calculators, let's test out that EXP key. We would just do 1.5 EXP 8, and that's it. That's all you got to do. If we wanted to, if you hit equals, it'll actually write the number out for you. If I wanted to, I could move the decimal place back 1, and I could also write this as 15 times 10 to the 7 kilometers. That's not wrong. It's the same thing. It's just a little weird. It's weird, but okay. And you can type that into your calculator. Same way. Ready? 15 EXP7, same number, okay? If you want to get extra weird, like me, You could even write 1 AU in the following way. I'm going to move the decimal point back to here. And I'm going to write 1 AU as 150 times 10 to the 6 kilometers. Let's put a box around this. This is the same as the other two, but the difference is that this is good math style. You're going to discover that when I write numbers down on the board, I'm often jiggling the decimal point backwards and forwards so that I can get a power of 10 that looks clean. Do you guys remember what 10 to the 6 is from the little table that I gave you? What's 10 to the power of 6?
1 million.
Exactly. So Brian, when I look at this number with my brain, if that was Brian that I heard from there.
Yep, that's me.
Oh, okay, you're in the last square here. Brian, when I'm reading this, I read it in my mind as 1 AU is equal to 150 million kilometers. I'm so fluent in math that when I see 10 to the 6, the word million pops into my brain as if I was reading Shakespeare. Okay, so eventually I'd like you guys to get like that too, but I'm pointing out that sometimes you're going to see me jiggle the decimal point around because I like to see things in terms of millions or billions or trillions. I think it's helpful for memorization, if nothing else. I want to try a little math exercise with you guys now. Hey there, Taryn. Nice to see you. I thought it would be cool. Taryn, make sure you try to, I know you're just getting in here, but make sure you get some of these notes down. They're important. Okay, I want to try a little math exercise with you. You guys know that today after lecture, we're going to be doing our first homework. And for some of you who are unaccustomed to doing science problem sets, these problems can seem really overwhelming and stressful. But it doesn't have to be that way if you have a cool tour guide like me who can teach you all the things that I've learned about problem solving. And that's what we're going to do right now. I'm going to give you guys a little fake math problem to work out, and it's going to have some deep, important lessons for this class. So see if you can stay with me here. What's the point of an astronomical unit? An astronomical unit is kind of like a meter stick for the solar system. We use it to measure distances between the planets. And let me show you a little diagram here to help with that. For instance, I could, if I wanted to, measure the distance from the sun to Mercury as 0.4 astronomical units. Now, I've got this weird habit where anytime I see a number between 0 and 1, I always think of it as a percentage in my mind. So if I see Mercury at 0.4 AU, Mercury is 40% of an AU from the sun. Venus is 70% of an AU from the sun. Earth is 1 AU from the sun, and the distance from the sun to Mars is 1.5 AU. Check out what happens when we get into the outer solar system. The distances become quite intense. Jupiter is 5 astronomical units from the sun. Saturn, 10 astronomical units from the sun. Uranus, 20 astronomical units away. Neptune, 30 astronomical units away. And Pluto's orbit is very squishy, but on average, Pluto is about 40 astronomical units from the sun. If you think of the entire solar system as like a disk, from edge to edge, the entire solar system is roughly 100 astronomical units. Actually, it extends beyond that, but I'm going to lie to you for now because it's easier to tell you lies than the truth. So let's just pretend that the solar system is about 100 astronomical units across. That means any two distances that you might want to measure in our solar system will always be a number between 1 and 100. And that's why astronomical units are good for us. They're useful. From time to time, we're going to need to convert units in this class. For instance, we know that Pluto's 40 AU from the sun, but there are times where I might want to know how far away that is in kilometers. So let's try a little problem together. You guys are going to get some schooling here. All right. I'm erasing this. Question. If Pluto is 40 AU from the sun, How many kilometers is that? Now, Mateus and Andrew need to pipe down here because they have an advantage over you guys. They have been trained in my methods, and I'm guessing that this is child's play for them. But for the rest of you, this might actually be stressful. So let's see what I'm working with. All those folks I'm talking to out there, before I show you how I want you to solve this problem, would any of you know how to do this? Let's say I was crazy and I gave you a pop quiz, and let's say this one question was going to determine your entire grade for the solar system, or for the stellar system. How many of you would be able to pass this class right now? Does anyone know what to do? Man, maybe that's a good idea, huh? Oh, Jay Wilcox, what's your first name? Because I just see Jay Wilcox.
It's Jessica.
Jessica, you know what I'm going to do, Jessica? If you don't mind, I just renamed you so that I'll be able to call you Jessica. It's going to help me. Is that cool?
Sure.
All right. So, Jessica, what would you do?
I would do the 150 EXP6 times 40.
That's right. And Jessica, you're having a good day today. If you did that, you would get the problem right, and you would get a 100 for this course if I made that the entire grade, okay?
That'd be good.
Yeah, that'd be nice, right? Then we could just log out and go back to sleep. Everyone from time to time is going to have a good day where they can see the problem in their mind and they know what to do, and that's always cool. But Jessica, those days are going to go away pretty quick, okay? We're going to be moving into some places that are just not so easy the first time around to think your way through. And I'll give you some demonstrations of that in a moment. And even if you're a math whiz like Walter, don't underestimate me. I can cook up a couple of problems that'll turn you upside down in no time. However, there is a method, my method, or the method, which can make problem solving so easy, and it's such a powerful skill. What I'm about to teach you goes so far beyond astronomy. It's not even about that anymore. It's about like life and having powerful skills. There's a method for solving these problems called dimensional analysis, which I swear and live by, and we're going to learn these techniques because it's good for you. Jessica, from now on, we're going to solve these problems in a different way, all right? First of all, I want you to make a note that this problem, it's a unit conversion problem. And I think that's worth mentioning. A unit conversion problem is when you have some number of, say, astronomical units, and then it's your job to convert it into some number of kilometers. This comes up all the time in life. You might have to convert dollars into euros, inches into miles, whatever. And these problems can get tricky, but they're easy if you follow some steps. I call them the 4 steps of dimensional analysis. And you guys are going to write this down. Use the 4 steps of dimensional analysis. This is a big deal, and I'm going to call on you later to look up these steps. So I want you to put a box around this and put some stars next to it and put some beams of fire coming off of it, because I'm going to need you to recall these from time to time, and I want you to be able to find them quickly in your notes. Okay. The first step is to write down the number to convert with its units. And I want you to write that statement down. Class, in this problem, what number am I trying to convert? What is the number that I would start by writing down? Maybe Jessica knows.
The 40.
Yep, but 40
AU.
40
units.
AU, Jessica, 40 AU with its units, okay? with its units. That's the whole point. All right, Jessica, let's do it using my methods. We'll start by writing 40 AU. Notice, Jessica, that 40 was not good enough for me. I need the units, okay? Step 2 is we are going to multiply by a division bar. And when we multiply by a division bar, we're going to do it like this. We do a times, and then we put a division bar just like so. I always make a fraction bar just like that. The reason for step 2 is that all unit conversions involve multiplication or division, but it can be difficult to figure out beforehand which is which. Now on to step 3. Step 3 is we're going to use the units to guide us. We put the units in first to cancel, all right? We're going to use the units to cancel them out. Now, at this point in the class, for the non-mathematically trained, I would like to remind you guys that every number is part of a secret fraction, whether you know it or not. Like if I write the number 5 down, the number 5 is
over 1.
Exactly. That's my point, is every number is always part of a secret fraction, and by nature, numbers are in the numerator. They're in the top of the fraction. And that means 40, even though it looks like it's in the middle, is actually on the top of a secret fraction bar. Therefore, I can cancel the astronomical units out if I place them over here at the bottom of a fraction bar. And we do that before we put in any numbers. And watch, now the AU's at the top and the AU's at the bottom, they cancel each other out. That's the secret to this game. Now on the top fraction, I put the units that I want to convert into, which in this case is kilometers. Now it's time for step 4, the last step.
Don't you need another division bar?
Nope, because here we're just going from AU to kilometers.
Oh yeah.
One
Sorry,
division.
my chemistry brought me back to that.
Yes.
So sorry.
In fact, I'll tell you something. I learned this technique from my high school chemistry teacher. And
Yeah.
of course, being 18 at the time when I learned it, this is what I did when she taught it to me. I did this. That's stupid. Okay.
Yeah.
Couldn't have been any more wrong. This guided me through so many years of physics that would have been too complicated for me to do. Physics, chemistry, freaking life. This is just a good skill to have. The wisdom of it will be borne out. You'll see. All right. So step 4 is put the numbers in second. Put the numbers in second using conversion factors. Sorry, I'm running out of board space there. That says put the numbers in second using conversion factors. In order to solve this problem, we're going to need to have a conversion factor in our back pocket, a conversion factor between AUs and kilometers. Do we have such a thing? What's our conversion factor? Does anyone know what I'm talking about?
KM, right?
Well, right, but there's a little more to it than that, right? A conversion factor is like, AUs equals kilometers, right? So you did the whole thing. What's our conversion factor?
1 AU equals 150 million kilometers.
Exactly, and usually you have that in your back pocket somewhere. You have it written down on a separate piece of paper, or it's in your notebooks with a box around it. We had that on the board a moment ago, but I have a very small board, so I had to erase it. Okay, so here's the secret. Step 4 has a little art form to it. You look at your conversion factor, and I'm going to try to do this with colors. This is going to sound so stupid. Don't be like 18-year-old me. This is not stupid, okay? This is sophisticated. You need to make sure that you keep the number next to its units when you place it into the fraction bar. So we're going to keep the 1 next to the AU and we're going to keep the 150 million next to the kilometers. So what I would do then is I'd put the 1 here, and I'd put the 150 times 10 to the 6 up there. And now we solve the problem using our calculators. Everyone, do this in memory of me. Take out your calculator. Anytime I punch, you punch. I need to make you strong, okay? So we're going to clear out our calculators. Let me, all right, I got some light here. So we're going to do 40, punch with me, times 150 EXP 6 equals. Hold it up. Oh, Taryn's got the hot pink one. I like it. To go with your hot pink neon lights, which I like too, by the way. Could you guys hold it up? I want to see that you got it. Okay, Walter, I dig it. Mia, I dig it. Jessica, I like it. Taryn, can you show me what you got? Just hold it right up to the little camera there.
Mine like died halfway through, so I have to like put it back in.
Yeah, it's probably because of the I like dim lights as well. So my apartment kind of looks like yours sometimes. There's blinky lights everywhere, but you might need a lamp or something, or in a pinch you can shine your phone lamp onto the solar panel. How about Kiana? Oh yeah, good. I'm happy. Kiana, you got this?
I wasn't here for the last lesson. What type of calculator is that?
Who's talking to me right now?
Grace.
Oh, great. Are you a troll, Grace?
No.
No?
I mean, I was here for like a minute and then my computer died and I had like a bunch of issues.
Grace, this is going to be a shock to you, but you are a troll. You just don't understand why. Trolls are people who don't share video with me. You're fine.
Sorry.
Okay, so if you're hiding in the background, you're like the troll under the bridge, okay? You can go through the
good
that way, but I'm going to call you a troll. So, Grace,
Great.
let me explain about trolls and let me explain about calculators. There's a particular calculator that you need called the Casio FX260 Solar. Thanks, Andrew. That looks good. I wrote it in the introductory email to you guys. I put it in the syllabus, and I mentioned it last time. By the way, Grace, I should mention something. If you and other people are in your shoes, you owe me something. You owe me Lab 1.
Yeah, I was wondering about that because you were talking about it.
Well, luckily for you, I recorded that class, and I posted that video. Like you couldn't help but bump into it here. If you go to the class Blackboard, look.
Amazing. Okay, awesome.
So you can watch that and you can do it. And by the way, you better do this because I don't want to see you start off with a 0 for your lab, okay? So I get
preferred,
it.
Yeah.
Yep. Okay. So you know what you've got to do. That's good. And by the way, get one of these calculators ASAP, or I can't train you. All right. By the way, the rest of you are looking good. Who was I talking to earlier about? Hey, Cheyenne, is our answer bigger than 1 million?
I'm muted. Sorry. It's bigger than 1 million. Yes.
Okay. So we better put that into scientific notation, right?
Yes.
Why don't you show me your chops again?
Okay. So the answer is 600 million. You move over the decimal.
False. It is not 600 million.
Did I read it wrong? I read it wrong. That's why. Sorry.
Let's put it into scientific notation first, and then we'll talk about it.
It's 6 billion.
That's
6 billion.
Right. Yeah. So how do I write that in scientific notation?
Lead number 6.
6.
Is it 6 times 10 to the 9th?
Excellent. And then we put our units down, which is kilometers. And once you're done, put a box around it because that's a classy move. That tells me, the reader, what you think the answer is. 6 billion kilometers. Nicely done. Okay, listen. At this point, Jessica might be like, dude, I had that done in 50 seconds. Why'd you got to play me like this and like make me do all this stuff? Wrong. Because this method does not take a long time. It just took a long time to explain it the first time. It's quick and it can help you solve very complicated problems. I wonder if we have time to try. I wonder how many of you could handle this. 12:53. I've got to teach you about angles, and I've got to teach you about scale models. This could be a worthwhile exercise. Okay, let's play a little game together. I'm just gonna burn 5 minutes to see who can handle this. First of all, how many do you guys have this down? This is very important. This could be the most important thing I teach you all semester. This is more important than what's a quasar or how many Tootsie Rolls are in a black hole. This is the most important thing. Okay, so let's erase this. Okay, we're going to play a game to see if you understood how to use dimensional analysis. And I'm just making this up off the top of my head. Suppose I told you that 15 stars was equal to 31 triangles. And then I told you that 17 triangles was equal to 9 squares. If I have, I don't know, 37 stars, how many squares is that? I want you all to take 1 minute of silence with a piece of paper and your calculator, and I want to see how many of you can answer that without my help using the steps of dimensional analysis. I already know that not all of you are going to be able to do it, but I'm trying to show you something. I'm showing you why what I just taught you is important. Take a moment and see what you can do. See if you can use the 4 steps of dimensional analysis. I'm going to solve it too, because I don't know what the answer is yet. I just made this up. I need some light here. Okay. I'll give you 1 more minute. Mateus, could you do it?
I'm able to do it.
Yeah.
You got it, Andrew?
Yeah, I got it.
How about you, Mateus? Were you able to do it?
No, not yet.
Oh, well, let's get on it, son. You know the methods. I just want to see who understands me, who like really understands me. Okay, listen up. You just learned an important lesson. There's a difference between listening to someone talk. There's a difference between watching TV and then doing a thing with your own hands. It's not the same, is it? Just because you hear me talk, just because you hear my words, it doesn't mean you understand them. Let's take a show of hands. How many people actually got any kind of an answer? Show me the hands. Andrew, Mariah, Taryn, cool. Philemon got an answer. Okay, but not everyone got an answer. Mateus, I thought you were going to knock this out of the park, but maybe we still have some things to learn. This is actually a good humbling experience, isn't it, Mateus?
Yes.
That's the idea. Okay, those of you who did get an answer, what'd you get? I got an answer. Mariah, what'd you get?
I don't know if I did it correctly or rounded correctly. I got 40.48.
I did not get that, but I could have made a mistake as well. We're going to do it together in a moment. How about Philemon? What'd you get, buddy?
73.44.
I'm sorry, say that one more time.
73.44.
Did you say 73?
Yes.
That's not what I got either. How about who else got something? Taryn. Taryn, what'd you get?
I also got 40.48 or 40.5.
I was doing mine fast and I'm a little sleep deprived today, so maybe I made a mistake. Why don't we do it together using the steps of dimensional analysis? Zach, I did not get that. Hold on, let me try this one more time. Let me just make sure that I didn't make a mistake here. Yes, actually you guys did, whoever got 40 or 40.5, you guys got it right. I made a mistake. So Mariah, you got 40, Taryn, you got 40, you guys understand me, that's cool. By the way, have you guys used dimensional analysis before? Is this your first? Yeah, okay.
Yeah, I've used it before.
Same.
That's it. So you guys probably have had some time to get why this is useful. The rest of you sit tight. We're going to show you how they did it. But this is an important lesson, a humbling lesson, okay? So let's check it out. And Taryn, let's talk to you a bit. And why don't you walk us through the steps of dimensional analysis, because you're a pro.
What was the answer? I think I got what was it, 40.9?
40.5, something like that.
Yeah, I got 40.4.
Good. Yeah, Andrew, I forgot to check up on you because you're a vet, so I figured you might have this. Taryn, why don't you do it with me using the 4 steps of dimensional analysis? What's your first step?
So it's probably not right, but I put 37 stars because that's what I thought was being converted.
That's correct. That's what the question is asking. This is, you write down the number to convert with its units, and its units are stars. So that's good. And then what did you do?
I put times, and then I put 31 triangle over.
No. I want you to go, you're probably good at this, so you're going fast. I want us to go slow, step by step, okay? Step 2 is we make the division bar. Step 3, and this is the secret, Taryn, we use the units first, no numbers, okay? So why don't you set up our units?
Sure. On the top, I put the triangle.
Yep.
And then on the bottom, I put the star in order to be canceled out.
Good. So notice that she's converting from stars into triangles. Now, I want to slow down here, Taryn, for those who are less experienced. Obviously, we want to get to squares. But Taryn, okay, Jessica, you watch this later and catch up with us, okay? I don't know what timestamp we're at, but you'll be able to figure it out. Thanks for participating. Stars into triangles, I just want to explain why she did that. She wants to get to squares, but she does not have a conversion from stars to squares. She can see that she has conversions from stars to triangles, and then another conversion from triangles to squares. So we're going to do a 2-step process here. First, she converts and puts stars at the bottom and triangles on the top. Now, if you want, Taryn, we could put the numbers in next, but where are you? I've lost your little face. Okay. You know what I like to do, Taryn? I like to set up all of my units and put the numbers in at the very end. I find that's like a cool way to do things. So why don't we go back to step 2? Let's make another division bar and tell me about the units that you did next.
All right. On the top, I put the square unit, and then on the bottom, I put the triangle unit in order to be canceled out again.
Lovely. So I use a slightly different color for that. So we are now canceling out the triangles. Okay. Now that her units are in good place, she's going to use these conversion factors. These are conversion factors, and she's going to place the numbers into the correct slots. So go ahead, Taryn, and show us how you did it.
So above the first division bar, it's 31 triangle, and then on the bottom is 15.
15 stars. Okay.
And then on the second division bar, on the top, I put 9 square, and then on the bottom, it was the 17 triangle.
Beautiful. And now, students, when we punch this in, because not everyone's going to know this, when we punch this in, we're going to do it all in one shot. Anytime something's on the top, we hit multiply. Anytime something is on the bottom, we hit divide. So we're going to do 37 times 31 divided by 15 times 9 divided by 17. So let's go ahead and punch that. And remember, I had gotten it wrong the first time around because I hit something funny. So hold on, I'm just illuminating this here. I'm trying to make it so that you can see my calculator. Okay, and the problem. Okay, so 37 times 31 divided by 15 times 9 divided by 17. And now, Taryn, let me ask you an adult question, okay? Were you here for the lab that we did on Tuesday?
No, I had to log off, but I reviewed the video that you posted from last semester.
Okay, so I probably made us think about this last semester too. What should we round this to be honest? Not all of these numbers are real.
Was it the 100th?
You're thinking about it the wrong way. You should think about it in terms of significant figures.
Okay.
How many significant figures do these numbers have?
They all have one or two?
2, 2, 2, and 1. Technically, Taryn, we should only round this to 1 sig fig.
Okay.
But I could maybe cheat and let you use 2. What do you think we should round this to?
We should round it to 40.5.
That's too many sig figs for me. That's
okay.
That's 3 sig figs, Taryn. That's cheating.
Okay. Then just 40.
That's right. And what are the units?
The square.
Do you have a parakeet?
I do. I have 2 of them, and they're not.
They're making a ruckus back there. I love it.
It's 40 square.
40 squares. That's right. Okay, nicely done, Taryn, and nicely done. Who's that other? Let me go back to Hollywood Squares here. Mariah and Andrew. I'm proud of you guys as well. I hope you guys took something away from that. A couple of you got a number. Philemon and Zach is a troll back there. Something happened with you guys. I hope you all figured out what it was. You're going to get many chances to do this, okay? So let's see what I got to work with. I got some time.
I
Okay.
have a question.
Yeah, hit me.
So I tried doing multiple ways. Do you want us to go in the order that you did it, like 37 times 31 divided by 15 and then times 9 divided by 17? Or do you want us to do it straight across? Because I got the same answer both
Right.
methods.
According to, let's see if I can pull some old math knowledge out of my head. According to the associative rule of multiplication, division and multiplication are equal in preference. So we could multiply across the top and divide across the bottom. One reason I didn't get into that yet, Taryn, is you need to divide by 15 and then divide again by 17. And I was worried that. But if you've got some chops, then, you know, I'm a musician, so when you have chops, that means you're good at playing the trumpet or you got some chops on the keyboard. If you're experienced in math, if you've got chops, then you already knew that. But I was worried the others might get confused. So we'll get to that in good time. But no, Taryn, it doesn't matter. The order in which you multiply and divide does not matter. The one thing I will say, Taryn, is I'm going to try to encourage everyone to punch it in one clean shot, kind of like you were cutting the head off of a snake. You just want to do it in one. So I don't want people like multiplying and then writing the number down on the margin. I just want to make it one clean shot. That's the right way to do things. Okay.
Thank you.
So let's talk about the solar system a little more, and let's talk about big distances. We had a discussion last time where we talked about what's outside the solar system. So what's outside the solar system?
Empty space.
For a while, it turns out, Taryn, that some of that space is not quite as empty as you think. Well, clearly it's better than the best terrestrial vacuums we can make in a chemistry lab. But as you start looking at the large-scale structure of space, you start to pay attention to even things like little tiny hydrogen atoms floating around. We're going to have to keep track of the very big and the very small at once. So I'm teasing you a little bit here, but it's not quite as empty as you might think. Eventually, you'll come to something else. What's the thing? Forget about the hydrogen atoms, Taryn. I'm just messing with you. If it's empty space, it's not empty space forever. Eventually you'll come across something. What will that be? Does anyone know?
Possibly star or galaxy.
What's the closest star to the sun? Does anyone know from science fiction? I don't know if you guys can see my collection of science fiction books and stuff, but I'm a little bit of a science fiction nerd. It kind of comes with the territory. The closest star to the sun is a famous star. Anyone know what it is? No? Not even Mateus or Andrew? I guess you guys just covered the solar system, so.
What? What was the question?
Oh, do you know what the closest star to the sun is? What's our neighbor star? I mean, I knew on Betelgeuse. Sorry?
Alpha Centauri.
Yeah, I knew there was some. Who said that? Who's that troll? Who's in the background there? Oh, that's Philemon. Sorry. Philemon. Yes, Philemon. And you just know that from maybe like watching science fiction movies or something, right? Or at least that's how.
Yeah, that was the movie from a long time ago. I don't know. These kids can see it.
Yeah.
Centauri, and it was playing a Space Invader game, and then you had to go out to space to save someone.
Yes. I love it. I love it. Yeah. These youngsters, they don't get it today, man, with their PS5s and stuff. All right. Okay. So I'm with you. Alpha, now Philemon, for the goal, do you know how far away it is in any unit?
4,000 kilometers.
No, it's definitely 4 something. It's 4 light years. Okay, but you remembered the 4. Here's the point that I'm trying to make. When you measure distances within the solar system, astronomical units are appropriate. Can I show you guys something? I want to just show you a picture of the Oort Cloud. And they should have one here with Alpha Centauri. I like this picture from Wikipedia. It turns out that the solar system is more than just the planets. There's a big giant cloud of icy comets that surrounds our solar system called the Oort Cloud. And here they're measuring distances, I don't know if you can see this here, in astronomical units. So for instance, here's the sun, right? And Earth is 1 AU away, Saturn is 10 AU away. This is a logarithmic scale, by the way, so it's changing scale as we go. Remember I told you the edge of the solar system is about 100 astronomical units away, but the Oort cloud actually surrounds it. This is 1,000 astronomical units, all the way out to 100,000 astronomical units. And once you get close to, not quite, but getting close to 1 million AU, you'll eventually come to the other star. Taryn, you can see why I was teasing you about space not being as empty as you think. There's all kinds of icy pebbles floating around out there that people didn't realize at first. So the thing is, Taryn, if you flew a spacecraft, your chances of bumping into any one of those snowballs is like 0%. It's still mostly empty space, but there is stuff out there. When we want to measure distances between stars, as we do in this class, astronomical units are no longer an appropriate unit to use. They're too clumsy. I'm going to now introduce another unit of distance for really big distances, for the distances between stars. It's called a light year. Let's take some notes. Introducing 1 light year. Oops, let's do this a different way. A unit for distances between stars, okay? Introducing a light year. A light year is confusing because it has the term year in it, but it's actually a distance. A light year, which we abbreviate as 1 LY, is the distance that light travels in 1 year. The reason we use light is because light is the fastest known phenomenon in the universe. Albert Einstein taught us that nothing can travel faster than the speed of light. So the speed of light is a maximum speed in nature. The speed of light, which we'll use many times in this class, gets its own variable, because it's a famous constant of nature, we call the speed of light c, and it has a value of roughly 300,000 kilometers per second. That's fast. Now, I had a little math problem, but I'm going to start running out of time here, and I have one more thing to teach you. I'm not moving fast enough today. I'm going slow because my brain is slow. But let's just write down what a light year is. 1 light year is 9.5 trillion kilometers. We're going to be using this conversion factor all the time in this class, starting in our homeworks today in a few moments. I've got so much to say about this, but I don't have time to say any of it. Class, I had a lovely little exercise intended for you about building a scale model of the solar system, but I don't have time for it because I have one more module to teach you. Luckily for us, the scale model problem that we're going to have to do in today's homework is basically just an application of dimensional analysis. So you actually know everything you need to know. It would have just been a fun little game to play. Today, we're also going to have to deal with angles. So I need to talk to you guys a little bit about angles. First of all, did everyone have time to write this down? Anyone need another second here? I'm going to have to erase this. Let me show you a picture. I got one last lesson for you today, if you can stick with me. Have you guys ever gone out, maybe, around October 31st, and as dusk settles, looked to the horizon and seen a big evil orange moon coming up over the horizon, and you're walking somewhere and you say, "Whoa, dude, the moon is huge tonight. Check that out." Have you guys had that experience before where you've seen the moon looking huge and evil and sometimes orange? You have been the victim of something called the moon illusion. And what you are seeing is somewhat a trick of psychology that is played on your brain, because your brain is kind of hardwired to understand angles. I might be close to 2 meters tall, but when you look at me, you do not see me as 2 meters. You see me as an angle. And this is like a funny thing that it takes a minute to wrap your mind around, but it's one of the most important lessons for astronomy. Check out Rainbow Ball here. Rainbow Ball is approximately 15 centimeters in diameter. But when you look at Rainbow Ball, you don't see it as 15 centimeters. You see Rainbow Ball as an angle, whether you look at it with your eyeball or whether this camera is looking at it. When Rainbow Ball is close to the camera, it takes up the entire field of vision. And as Rainbow Ball gets farther and farther away from the camera, the angle which it subtends becomes smaller and smaller. And the lesson for you guys is that you don't see sizes, you see angles. I want to write that down. Let's talk about angular size. The symbol that I'm going to be using for angles in this class for now is the Greek letter theta. You don't have to speak Greek. You just have to be able to make a 0 and put a line through it. We like to use Greek letters for angles because the Greeks taught us to love geometry, and we do it in memory of them, okay? Let's draw a picture of what it looks like when you stare at the moon. The moon has a circular or a spherical shape, and it has some diameter, just like Rainbow Ball does. We're going to be calling the diameter of the moon, or the diameter of our star, S. You can think of S as standing for the size of the moon. But really, it stands for the diameter of the moon. And it's usually measured in units of kilometers, but not always. You are looking at the moon from some distance away. Here's the observer eyeball that I'm going to draw. And the moon will subtend some angle in your vision. This is the moon's angular size. So this is the angular size. And typically the units that we use for angles are the degree. So it's the angular size measured in degrees. As you saw me move Rainbow Ball towards and away from the camera, you may have realized that the distance determines how big an angle your object will subtend. So let's draw that parameter in as well. From the moon to the observer on Earth, little d, we always use lowercase d for distances. That's just common. Little d is the distance, and usually we're going to measure that in kilometers as well. These three quantities, the distance, the size, and the angle, are related to one another by a famous formula called the small angle formula. Let's write that down. The small angle formula is one of the key formulas that you need to know to understand how astronomers think. It tells us that the size of our moon, or the size of our rainbow ball, is the angular size times the distance times 2 pi over 360 degrees. I'd like you to put a box around that. We'll be needing that today. This is known as the small angle formula. It's a key concept. All right. Mia, let me know when you're done.
I'm not done yet.
Oh yeah, Andrew, you too. Let me know. Cool. Andy, let me know when you're all set. I've got just a little bit more, and then we can take a break before the homework time.
All right, I got it.
All right, everyone else cool? All right. Let me show you some pictures here. I haven't actually finished explaining the whole moon illusion thing to you. So next time you guys see one of those big evil moons, you could try it. I think the phase of the moon right now is waxing crescent, because I can see it early in the evening. But I want you guys to go out next time you see one of those big moons on your horizon. It's always going to be on your horizon when this happens. And you'll hold your arm outstretched, and you'll put your finger up against the moon, like put it in front of the moon. Your finger, when it is outstretched away from you, subtends roughly 1 degree on the sky, okay? And what you'll notice, if you actually go out and you compare your finger to the size of the moon, even when the moon looks big and evil, if you hold up your finger to the moon will be roughly half the diameter of your finger. Now, you put your finger away and you go about your business, and later on at night, the moon will get higher in the sky, and it won't look huge anymore, and it won't look orange. It will look white. Take your finger out again and hold your finger back up against the moon. You'll discover the angular size of the moon is the exact same as it was before, half the width of your finger. Your brain will have a hard time understanding that, but it's the truth. You have to measure it. The reason why the moon looks huge when it's on the horizon is your brain is hardwired to understand angles. When you're seeing the moon rise, you're seeing it against a foreground of trees and mountains and cactuses and skyscrapers. And your brain is hardwired to say, holy shit, if that thing is half a degree, if it's half the width of my finger, and it's behind all of that stuff, then that glowing orb must be insanely big. And think about why that makes sense, right? If you're out in the forest and you see a little tiny bear on the horizon and the little tiny bear is running towards you, your brain needs to know that by the time the bear gets up to you, it's not going to be a little tiny bear anymore. It's going to be a big scary bear. So you need to run now. So your brain knows when something has a small angle, when it's far away, as it gets closer to you, the size will grow, right? So I'm saying this badly because I'm sleep deprived, but in any case, your brain knows that the moon is big only when you can see it against a foreground of trees. Later on in the evening, when you see the moon pasted up in the sky, you have no depth perception whatsoever. And if you think about it, the moon doesn't look big or small. It's just kind of there. You have a hard time gauging how big it is when it's higher in the sky. This is known as the moon illusion. You can read about it in Wikipedia. It's super cool. It's a nice illustration of one of the issues we have to deal with in astronomy. Everything that we look at, we see in terms of angles. And check out a couple of slides here from my slideshow. We can talk about the angular size of an object, like the moon, or later on when we learn to measure the distances between stars, I may even want to talk about the angular separation between two stars, like a binary star. We'll get there soon enough. Don't worry about it. Remember that generally the unit that we like to use at first is going to be the degree. A degree is 1/360th of a circle. It turns out that your hand can be a tool that measures degrees in a lot of different ways. Your outstretched finger is about 1 degree. Your outstretched fist is about 10 degrees. And if you do that Hawaii thing, the hang 10, that's about 25 degrees from thumb to finger. And oftentimes astronomers will use their hand as a crude angular measurement tool. However, consider this. Let's write this down. The angular size of the moon is approximately half a degree. And by a curious coincidence, the angular size of the sun is also half a degree. Think about that. Students, is the sun the same size as the moon? What do you know? No way, right, Kiana? What's bigger, the sun or the moon?
Sun is bigger than the moon.
What's closer to Earth, the sun or the moon?
Oh God. I think it's the moon.
It's the moon. The moon's closer to Earth. Doesn't that seem weird, Kiana? Like a weird coinkydink in nature? That the sun is bigger than the moon, but the sun is like farther away than the moon by just the right ratio, that the two objects end up having the same angular size. And what does that mean? Well, it means cool stuff because, as you guys know, on certain times or certain dates, when you have an alignment, you can get the awesomeness that is a total solar eclipse. A total solar eclipse occurs when the disk of the moon perfectly covers the disk of the sun, and the disk of the moon blocks the sun for the most part, leaving behind an eerie glow from an outer layer of the sun called the corona. This is a total solar eclipse, and maybe we'll talk more about that later. Notice the disk of the sun is being covered by the moon. This bit is an outer wispy layer of the sun that you normally cannot see during the daytime because the disk of the sun overpowers it. People who study the atmosphere of the sun actually like solar eclipses because then they can actually get a look at this coronal light. Of course, you guys will remember that today we learned that the Earth actually varies in its distance between the Earth and the sun. There's perihelion and aphelion. The moon also has a slight variation in its distance. Sometimes there are very rare types of eclipses when the moon is a little bit farther away from Earth and its angular size will shrink by a tiny bit, and you can get a very rare and magical type of an eclipse known as an annular eclipse. Let me show you a quick picture of that. So here's like, I don't know, people make a big deal out of taking cool astrophotos of annular eclipses, but here's one here. I don't need the most perfect picture. So you can see here, the angular size of the moon is just less than half a degree, and you get this little annulus, or this ring of fire that surrounds the sun. Sometimes it's lopsided. It's very beautiful. These are a very rare type of an eclipse. I believe there's going to be an annular eclipse that passes through Vermont in 2025. So 5 years from now, you might actually get a chance to see one if you're willing to drive to Vermont. I'm thinking about doing it. I'm guessing the hotels are already booked up, but whatever. Pitch a tent or something. Last bit, and then we're going to take a pause. I know you guys are probably getting tired. I have one last little note thing to put on the board, very quick. Because the sun and the moon are the largest two things on the sky, astronomers frequently need to use smaller units of angle. So I want to put those down before we take a break. There are 3 units for angular size. And we're going to need this for our homework today, which is why I had to squeeze it in. So the first unit that we've already considered is the degree. And 1 degree is 1/360th of a circle, okay? Or in other words, I can write down this conversion factor, which is a little funny. 1 circle is equal to 360 degrees. Normally, a degree looks like a small angle when you're looking at a piece of paper. But in astronomy, the circle is the sky. So a degree is quite big and clumsy. Introducing 2 smaller units of angle. The first is called the arc minute. And the abbreviation for arc minute is 1 with a little apostrophe after it. An arc minute is defined as a 60th of 1 degree. So we're going to take a degree, we're going to zoom in on it, and we're going to slice it 60 times until we have really, really tiny little angles, okay? And we can say that 1 degree contains 60 arc minutes. That's how we write down our conversion factor. An arc minute is approximately what you get when you try to look at a soccer ball from half a mile away. So if you had a soccer ball half a mile from you, that round soccer ball would subtend 1 arc minute. 1 arc minute is approximately the angular size of Jupiter on your sky. Sometimes we need even tinier units of angle, and that's when we break an arc minute down into 60 more wedges. So then we'll take an arc minute, we'll break it down just the same, and you get something called an arc second. An arc second is a 1 with quotations after it, or 2 apostrophes. And it's defined as 1/60th of 1 arc minute. Or in other words, 1 arc minute contains 60 arc seconds. Now, you guys had to get this squished in at the end, and I know you're probably getting fatigued just listening to me talk. That's natural. But we're going to need these for our homework today, so I wanted to make sure we got them into your notes. We're going to use these things all the time because astronomy is all about angles, okay? I'm at 128, so I'm doing pretty good as far as time slot goes. I'll just mention one last thing.
I think you might be a couple minutes behind because my computer and my phone both say 1:33.
Oh, geez. Yeah, what's up with that? My stove, all my clocks have different time. Oh, you're right. Okay, well, you know, I don't know if we have to be that careful about. I gotta
Well,
tell you.
yeah, it doesn't matter. I was just
Yeah.
letting you know.
No, I appreciate that. Actually, I noticed that the other day. Guys. One thing you're going to learn about me is I'm not good at punctuality. It's not one of my strong suits, and I'm trying to get better. But as the semester goes on, you guys are going to learn just how not punctual I am, and it's going to be sad. Okay.
Oh, I can't see the rest of the board.
Oh,
I'm
sorry,
still
Andrew.
trying to copy it.
Guys, last class we had a little pause, a little break between the lecture and the lab, and now it's going to be time for us to do our first homework assignment together. Do you guys want to take that little break? Was that helpful for us psychologically? Most people are nodding. Okay. Yeah.
Do you think you can leave the stuff that's on the board though? While the
Yes,
break's going
Brian.
on?
I'm planning on doing that.
Thank you.
Okay, Walter, but just check this video later and do the homework. In a sense, what we're about to do is the most important part of today. The homework is the real work where we earn points. And I know that's tough, but that's the nature of the class. Consider this: you can do it with me now, or you can try to do it on your own later, and that's not gonna be fun. So we got to get this done. Let's take a little 15-minute pause. I'm going to pause the recording, and when we come back, we're going to read the problems. We're going to solve the problems together, and you'll be able to turn that sheet of paper right in, and you'll have all your work done for the week. Okay. Okay. Welcome back, astronomy, to your very first office hour session. Let's see if I can get some of you to share some video with me. Oh, I had a stupid song I was going to play, but it's not necessary. Okay. Hi, Tegan. I just had a question from Grace, who's trolling in the background there. And Grace just basically asked me a question that many of you have been asking me, which is, so I thought this class was supposed to be asynchronous, and now you're teaching these live lectures. Oh, is that you, Grace? Can I see you now? Welcome to humanity. Okay, nice to see your face. Nice to see all your faces, Amy and Tegan. Yeah, cool. Like, nice to know that there's some humans in the background there. So Grace is like, what's up with that? And of course, every professor, you know, they went through all this trouble to make the block schedule so that you guys could stagger all your courses. And now it's like the Wild West again. Well, as I was explaining to you, Grace, I already have these lectures recorded. In theory, you don't even need to, I mean, you need to do work and you need to watch the videos, but notice that below this line, older videos from fall 2020, I have, like, this is the class that we essentially did on Tuesday. And this is the class that we did today, including the office hours that we're about to do are on here. So Grace, I'm kind of done. Like, I could just stop this recording and I could go take a nap. And to be honest, that's really, really appealing right now because I'm a little tired. But I'm not going to do that, Grace, because I figured that you guys might want the opportunity to actually interface with me. Now, of course, Grace, because I have like 168 students, there's no way that I can pick a time that's going to work for everyone. So what I decided to do was pick a time that works for me. And since I'm not an early riser, I decided that noon would be a cool time to start. Now, probably every other professor is doing the same thing, right? I certainly didn't want to start this class at 8 a.m. I would fail you. I would not be able to do that. I even had this crazy idea today when I was waking up, that maybe it doesn't even have to be a set time. Maybe one of these weeks, if we're feeling crazy, I could hold the live lecture at like 6 p.m. so that some of the students who are working during the day could do it. But I suspect people will attend even less if it's at 6 p.m. because then they got to pick up their kids and make dinner. And some of you work nights at the supermarket or something. I'm guessing, well, you guys are here, so probably this time slot kind of works for you. So Grace, I would say I'd hope your other professor who's having classes is also recording them. Are they doing that?
I'm not sure yet. I haven't actually, we haven't had a class yet because he's only on Thursday. So I'll be able to like attend the Tuesday one. That's fine.
It's a Thursday one. So maybe hang with us live on Tuesdays.
Yeah, then, I was planning to anyway.
And do your other class on Thursdays. And then remember, After this office hour session, it takes me 1 hour to render the video, and then I put it up online. I have to tell you guys that there was a hiccup on Tuesday's video. Probably none of you watched it because most of you were here live, but it took me like 3 hours to render the video because YouTube crashed and things got, so I didn't actually get it up until 7 p.m. and I think that stressed some people out, but it was just the way the cookie crumbles. In general, it takes me 1 hour for the video to render, and then I get it right up on YouTube. YouTube takes about 30 minutes to process the video, and then I can post it.
Yeah.
So this video will be posted. So I'm doing the videos, Grace, all over again, so that if you can watch them, I think it's kind of cool to develop a camaraderie with your classmates. Like your classmates are Mateus and Tegan and Philemon, and just kind of seeing each other's friendly faces is kind of a nice aspect to this. But you can also watch last semester's video with no loss of content. I just think I offer this as a service to you. This is bonus. Me offering to hang out and do the work with you so that you can ask me questions like you are. You see what I mean? But it's the live session. It's not an obligation. It's a bonus, right? However, you are obliged to give me 1 lab per week and 1 homework per week, and I need them by Saturday because I'm grading all papers on Sunday. I'm going to stress this once again. Once Sunday at midnight hits, or I guess Monday at midnight hits, I'm closing the submissions for lab 1 and homework 1. So you have until then to get this done. We're going to do our homework now. Okay. So let's get to this.
I have to head out. I'm sorry.
You have to go to your other class, right?
Yeah, I'm sorry.
So Grace, that's okay.
It's the first class.
Yeah, of course. I don't want you to miss that class. But Grace, no matter how tired you get or how distracted you get or how many bowls of Cheerios you eat, make sure to go back and watch this video and do this homework session and turn it in, okay? I'll be keeping an eye on you. All right. Bye, Grace. All right, the rest of you ready to crank out this homework? All right. So let's do it. First, the thing I need you guys to do is remember that I've provided the questions for you in case you do not have a book or your book hasn't come in or whatever. If you go to the homework tab, this is where we'll be submitting our homework. Let me make sure this is available. Oh yeah, all right, it's available. So this is homework number 1. We've got 2 problems from chapter 1, 3 problems from chapter 2. And if you guys right click, you can open up the PDFs with the scans of questions. And I'm going to be asking you guys to read the questions, and I'm going to show you how I want them done. All right, so we're going to do this together. First of all, you're going to be turning in or photographing this work. You can do it in your notebooks or you can do it on a separate piece of paper, but I want it to be formatted in a particular way. I care about the formatting. It would be nice if you could use pencil, but as long as it's clean and neat, I won't complain too much. Where's my marker? Hold on a second. Is this it? Nope. Hold on, guys. I'm losing my damn marbles here. I need that. I guess oh, is this it? Yes. Okay, cool. Sorry, I am totally out of whack today. All right, let's erase this. I'm going to show you how I want it formatted. And this is how you would submit things to me, whether we were doing a live or a virtual class. But first of all, at the top of the page, be classy about it. Start a new page. All right, paper's cheap. Let's do name. So you put your name down. I want you to put astronomy 1020. And then could you guys put your section afterwards? Like, for instance, Amy. What section are you, Amy?
102.
So if I was Amy, I would do 1020, and then after it, I'd do 102. You guys are either in section 001, 002, or 102. I don't know what your section is. And then up here, you're going to put homework number 1, because this is our first homework. This will be good for you to keep track of what you have submitted, especially when you're studying for the test. And from chapter 1, we're going to be doing problems. Let's see what they were again. chapter 1, 42 and 49. From chapter 2, '53, '55, '58. I want to get right to this. Mateus, are you still with us?
Yes, I'm here.
Mateus, I'm going to ask you to read the first question because you know my styles.
Yes.
But eventually all of you will be called on sooner or later to read a question so I can hear your lovely voices. Do you guys see this formatting? You're putting that down? You're going to be turning this in. So you're going to do everything that I do. Our first question is chapter 1, number 42. And Mateus, you know how it goes. I like to hear the title too, right?
Yes. So let me know when you're ready.
I'm ready for you.
Okay, so scaling the local group of galaxies. Both the Milky Way galaxy and the Andromeda galaxy M31 have a diameter of about 100,000 light years. The distance between the two galaxies is about 2.5 million light years. Do you want me to stop here?
I sure do. You know my style. Students, notice that I'm extracting what I call the givens, the technical information from the problem, and you should be doing the same thing. The reason why I'm stopping him, and he probably knew this, is they wrote out the word 2.5 million light years. We want to put this into numerical form. Hey, Tegan. You with me?
Hi.
Tegan,
Yes.
how should I write down 2.5 million light years in scientific notation?
Would be 2.5 times 10 to the 6th. Sorry,
Beautiful.
not good with numbers.
No, you are good. You did that just right. And I
Hey,
could have
yay.
asked Mateus, but Mateus is more experienced having been through my solar system class. I wanted to pick a random person and see if they could do it. And you did great, Tegan. Thank you. All right, so Mateus, keep going.
All right, so A, using a scale on which 1 centimeter represents 100,000 light years, draw a sketch showing both galaxies and the distance between them to a scale.
We actually have to make a drawing here, students. I'm serious. Like, I want you to make a drawing to scale. That's the problem. Now, I might have suggested to you guys last class that it would be really freaking cool if you could all shell out 59 cents and buy a cheap-ass job lot ruler. How many of you actually did that? Let's see, how many people actually have a ruler handy? All right. Yeah. A couple of you are making me proud. Amy, I like it. Mateus, do you have one? Mariah's got one? Cool. It's a simple thing. Now, the rest of you guys who don't have one, you're going to have to struggle a little bit harder. You have to find some way to do this, okay? This is your job. Now, this isn't a very expensive instrument, so the next time you're out at the convenience store, hell, you could probably get this as a bloody gas station, or, well, maybe that's too ambitious, but you could get this at Staples or Job Lot or wherever. CVS probably
Can I
has
go
it.
grab my ruler really quick?
Oh, I like it, Mia. I'm sorry, say that again?
Can I go grab my ruler really quick?
Yeah, we'll wait for you, Kiana. Go grab it.
Thank you.
I'll sip some ice water. Okay, hey guys, a lot more of you had a ruler than I thought. Walter, Brian, people who might not have a ruler. Oh, you got it, Walter. Awesome. If not, you might find something around that you could use as a straight edge. The edge of a book could work if you're in a pinch. I like this one because it's clear. It's nice for measurement. I borrowed this from the astronomy lab. All right. Anyways, we won't get going too quick. Don't want to stress out Kiana here. We're going to need some space across our entire page, this scale model, okay? Let's wait for Kiana, as I promised. Astronomy dance party. All right, Kiana's back.
Sorry about that.
That's okay, buddy. We don't mind. We're all in this together. Okay, I'm going to point out a couple of things that aren't going to be obvious to you. I'm going to show you how we're going to draw our galaxy here. We want to make a galaxy, a scale model of a galaxy at which the Andromeda diameter and the diameter of Andromeda, the diameter of the Milky Way and the diameter of Andromeda are going to be 1 centimeter. And then we're going to have to figure out how many centimeters apart to make these galaxies if they are truly separated by 2.5 million light years. When you make a scale model, you are basically inventing your own conversion factor. And we sometimes call this in map making, this is your scale factor. Our scale factor is that 1 centimeter on our drawing will be equal to 100 million light years. I want you guys to notice this next pro move that I do. I'm going to put a prime, an apostrophe, right above the centimeters. The reason why I'm doing that is because, remember, students, centimeters are a real physical unit, right? And I can convert centimeters into meters. I can convert meters into kilometers, and I can convert kilometers into light years. That means there's an actual number of centimeters equal to 100,000 light years. And let me tell you, it's not one. There's a lot more centimeters in 100,000 light years. This can lead to some hideous confusion if you're not careful. So the purpose of the prime is to say, these aren't real centimeters. These are fake centimeters. These are on the scale drawing on the page. And you'll see as we go forward why the prime is so important. Okay, let me show you how to make a little galaxy. Up at the top, near where you put your name on the page, I want you to make a line that is 1 centimeter, exactly 1 centimeter across. Okay, so measure it with your ruler. And to make a galaxy, you can put a bulge in the center, and you can put 2 little spiral arms on it, just like that. That's how I like to draw galaxies in my astronomy class. Make sure this is 1 fake centimeter. And I'm going to label it as such. The reason why I'm putting it in the upper corner is going to be obvious in a minute. So I'd like to talk shop with, well, you know what? Let's talk shop with Mateus, I guess. Because Mateus, you actually did struggle a little bit during our conversion factor problem today, right? So this could be a good reminder for you, but you'll also be able to figure it out. So Mateus, here's our problem. We know that 1 centimeter is equivalent to 100,000 light years. Our job now is to figure out how many centimeters would be represented by 2.5 million light years. What's the technique that we're going to do to figure that out? Sorry?
Yes, got it. So you're going to put down 1 centimeter first?
No. What is the first step in dimensional analysis?
Oh, I know.
What is it, Andrew?
Write down the numbers to convert with its units.
Right. And what are we trying to convert here?
So you're converting the 2.5 times 10 to the 6 light years
into
into
centimeters, right?
Yeah.
So Mateus, it's not 1 centimeter. We already know how many light years 1 centimeter is equivalent to. We need some, and this is an important lesson, Mateus. Sometimes it's not obvious what you're trying to convert. You have to kind of pause and think about that. Mm-hmm. So we're going to start by writing down 2.5 million light years. Okay, Mateus, what's the next step?
All right. And then you're going to do 1 centimeter on top. No.
Mateus, for the benefit of the class, we're doing this by the numbers. I want you guys to not think. I want you to follow the 4 steps of dimensional analysis. There's a reason, there's a madness to my method. Step 1 is, according to Andrew, write the number down to convert with its units. What's step 2? Look at your notes if you forgot. The 4 steps of dimensional analysis. We're doing dimensional analysis, right,
Multiply
guys?
by a division bar.
Thank you. Multiply by a division bar. That's step 2. Okay. Now, Mateus, what do I do?
All right, so now you're gonna put the 1 centimeter on
Holy
top and
shit, no. You
No.
just, no, you can't play with numbers. You can't talk to me about numbers because that's not step 3.
Oh, you're just doing
You're not allowed
the
to even-
units right now. I
You're not
know
even
that's the last
allowed
thing that
to
you do.
talk to me about numbers. Mia, what do you think I should do?
Put units in first that to
That's right, we
cancel.
put the units in first. Okay, show us how it's done, Mia.
Oh, jeez. Okay, so you're gonna put light years on the top right. Oh, I'm sorry, the bottom corner.
Wait, which is it?
The bottom right. I'm sorry.
Yeah, okay. Otherwise, they won't cancel, right?
Yes.
All right.
And
what's
then
on top?
if you want to bring it into centimeters, you can put centimeters in the top corner
Fake centimeters.
on the right.
Okay. That is step 3. Now, Mateus, I know that you were doing it right, but that's not the point. You need to do it these steps. This is for everyone, okay? Okay, now what do? I gotta put, now light years will cancel. And now what's step 4?
Oh,
Put in
step 4.
person.
Anyone, it doesn't matter. Just tell me what to do.
All right. Put the numbers in second using conversion factors.
Okay, so put some numbers in.
So up top is going to be 1
Yep, 1
centimeters, and then 100,000 at the bottom.
Good. Okay, guys, punch them up and tell me what you get.
Oh, I already got it.
Oh, do you have a cat too, Taryn? Taryn, does your cat ever want to eat the parakeets? Is that an issue?
Not this one. She's pretty good about them, but I have another one, and he's like determined to get them.
I bet that's like having two gummy bears just floating around in the sky for him. He must think about that a lot. One day you're going to log in and it's just going to be feathers everywhere. All right. What did you guys get?
25 centimeters.
Good. Let's write that down. 25 fake centimeters. Centimeters prime. Okay. That tells us the separation between the 2 galaxies should be a line that's 25 centimeters. Now, you're going to need your whole page probably to do this. And I want to see this on your page or you won't get your 5 points. Go ahead and make a line that's exactly 25 centimeters, and you better make it really 25 centimeters. I know the difference. I'll know if you're cheating. I'll measure it. Okay? So make it 25 centimeters. You probably have to go diagonal across the entire page. And then what we're going to do is we're going to draw in the Andromeda Galaxy, make another line that is 1 centimeter. Okay. Make another 1 centimeter line, and then you can put a bulge and some spiral arms on that too. And there's the Andromeda Galaxy. This is 25 centimeters.
I'm just gonna say this is hurting my OCD.
Oh, because it's cutting through the stuff?
Yes.
In that case, you are free to use your own personal style. You could use a whole nother page or the back of the page. You just have to scan it. In my case, who was just talking to me? Who's the OCD person? Because I respect that. Who are you?
It's okay.
Oh, that's Mia. Yeah, Mia. Oh, it's Mia. I only have this one board to work with, so actually, maybe it's kind of cool. It's kind of like abstract art. We're slicing through the numbers. Okay. By the way, this is part A, so make sure you label it part A. And now we've earned 3 out of 5 points. You got 1 point for the conversion, 1 point for putting the galaxies the right size, and 1 point for doing the line the right length. Each problem of homework that we do is graded out of 5 points, and I usually have preconceived ideas about what each point is for. So for part A, it's 3 points. For part B, it's 2 points. And of course, if you follow along with me, you're going to get all your points. Just don't miss anything. Don't forget anything. Okay, once you're ready, Mateus, you'll read us part B.
I actually have a quick question before we do that. Is that okay?
Yeah, that's fine. Shoot.
Do you mind just going through the Casio calculator and like showing me the process of doing like the canceling out and everything like that?
That's actually a great idea, Mariah. I forget that can be really helpful for you guys. So let's do that. And there are probably others, especially later on. So my plan is I'm going to do this. I don't have to multiply by 1, Mariah, because that's a waste of time. But if it's in the bottom, we're actually going to divide here. So I know it says times, but it's basically this means take this and divide it by that. So here's what I would do. Okay, so let me activate. Let me clear out. Let me get some solar energy here. Okay, so I would do 2.5 exp6 is times 10 to the 6, right? That's probably what you did wrong, right? And then divide by 100,000 equals 25.
Yeah, I kept getting 250 because I did 10 exp6. That's why.
Yeah, that's a common mistake. Remember, the exp includes the times 10. So you just learned a very important lesson. And thank you. Thank you. Probably other people watching this video later will benefit from that. Okay, Mateus, we ready to do some part B?
Yes. How does the separation between galaxies compare to the separation between stars? Based on your answer, discuss the likelihood of galactic collisions in comparison to the likelihood of stellar collisions.
Okay, there's 2 parts to this. The first part is, how does the separation between galaxies compare to the separation between stars? Now, Philemon, do you remember how far away? Let's take the Sun and Alpha Centauri as 2 typical stars out there in the galaxy, right? Philemon, do you remember how far away Alpha Centauri was?
4 light years.
Yeah, technically 4.4, but 4 is good enough. So it's about 4 light years from the Sun to Alpha Centauri. And let's assume that our star is an ordinary garden variety star that's not too unlike other stars in the galaxy. That means the typical separation between stars is something like 4 light years. So Philemon, how would you say the distance between stars compares to the distance between galaxies? No tricks, just a simple answer here. Here's the distance between galaxies, and we know that Alpha Centauri is 4.4 light years away, right? Oh, that's the symbol alpha. Rather than write it out, it's a little Jesus fish, whatever.
0.4 2.5 times 10 to the 6th.
I'm sorry, could you say that once more for me?
4.4 light years times 2.5 times 10 to the 6th.
No. What we're looking for here is just a qualitative order of magnitude description. Galaxies are 2 to 3 million light years away. Stars are separated by like 4 light years. So in general, we can say, assume 3 and 4 are the same distance. The difference is this, it's the order of magnitude. Does anyone understand what I'm trying to say? I think I may have confused you intentionally.
So you don't do the 2.5, you just do the 10.6?
Not 10.6, 10 to the power of 6.
10 to the power of 6, sorry.
Yeah. Philemon, if you've only taken like sort of pedestrian math classes, you're used to there being a big difference between, say, 3 and 3.14, and God forbid you should mess those up. Astronomers do a kind of sloppy Wild West math, a math where you kind of squint your eyes and you try to see the big picture of things. Order of magnitude means I have hundreds of more jelly beans than you have, or I have thousands of more jelly beans than you have. You don't worry if you have 3,271 more jelly beans. You're just kind of thinking sizes. If you compare distances to galaxies to distances to stars, what would you say? Maybe I'm being too, maybe I'm hurting.
Yeah, I haven't done that since like 1992. There's been a little bit more of a other substances besides that.
Yeah, I understand. I understand, son.
Are you saying that galaxies are farther away from each other than stars are?
Yeah, by roughly what factor? Was that Taryn I was just hearing from? Who talked to me just now? Oh,
It was Mariah.
Oh, Mariah, are you a troll or are you there? Wait.
No, I'm here.
Oh, where are
I'm
you?
here.
Oh, yeah. Hi, Mariah. Sorry, you have the cool vines. I'm sorry. I had. When I'm in speaker mode, I can only see 2 to 3 faces at a time. Mariah, yes, I am saying that galaxies are way farther away, but rather than just saying really farther away, of order, how many times farther away are galaxies compared to stars?
Is it 10 to the 6th?
All right, translate that into English now.
Oh wait, I know this. Give me a second.
Yep. Now you get it.
Is it a million or mega?
Yeah. So what I'm trying to extract from you is, in general, galaxies are millions of times farther apart than stars. That's what I was trying to say. Let's write that down as the first part of our answer. In general, galaxies are millions of times farther apart than stars. That's your fourth point. Okay, I got lost there. Mateus, what was the last part of this question?
All right. Based on your answer, discuss the likelihood of galactic collisions in comparison to the likelihood of stellar collisions.
Okay. In other words, let me simplify that. They're saying, what's more likely to collide, galaxies or stars?
Stars.
Yeah. It seems like that's what they're getting at, right? Except that's totally wrong. I understand why you said that. It's just not right. Because this question is more subtle than it seems. Okay, can I make sure everyone's got all this? Because I need to erase for the thing I'm about to do next. Andrew?
Yeah, you're all set.
All right. It's not just about how far away things are. It's also about how big the things are. In a way, colliding stars and colliding galaxies, it's like rolling a couple of these marbles across the floor. I could stand at one end of my apartment with one of these ball bearings and one at the other end, and I could put a blindfold on and I could roll them towards each other. And what would be the probability that they bumped into each other? Well, it depends not only how big the room is where I'm rolling them across the floor, but it also matters how big the marble is, right? So let's think about what we've learned in part A. In part A, you learned that galaxies are separated if their diameter is 1 centimeter, their separation is 25 fake centimeters. So basically what that means is there's a 1 to 25 ratio diameter to distance ratio for galaxies. So galaxies are 25 times farther apart than their diameters. Don't you think it's interesting that they asked you to do this for galaxies, but not for stars? What if they had asked you to do this for stars instead? Our sun has a diameter of 1.4 million kilometers. What if we had made the same scale factor? And what if we had tried to set the sun equal to 1 fake centimeter in diameter? And then we asked the question, how far away would I go to get to the next star, Alpha Centauri? Now, normally I like to have the students do this, but I want to speed things up because we have a lot to do today. So I want you to watch me do it and fast forward, okay? I know that Alpha Centauri is 4.4 light years away. But if I want to convert that into fake centimeters, I'd have to do a little bit more work because I'm converting kilometers to centimeters there. So I'd say 4.4 light years. And first I would convert light years into kilometers. And then I would convert kilometers into my fake centimeters, my paper mache centimeters. Today we learned that 1 light year is 9.5 trillion kilometers. And we've made a scale model in which 1 fake centimeter is equal to 1.4 million kilometers. Class, go ahead and punch that up for me. I'm sorry I had to do that in fast forward, but we have a lot to do today. Can you guys punch that in?
I don't know if I did it correctly. I got a really big number.
That's what you should get. What's your number?
It's 1.79142857 to the 14th.
Human calculator. Not times 10 to the 14th. That doesn't sound right. Usually I want to give 2 sig figs followed by a times 10 to the something. All right. What'd you get?
I could have put this in wrong. I got 2.985714286.
How about 3?
Big.
Just call it 3.
Yeah, 2.3. Yeah, or
No,
3.
no, just 3 times 10 to the what?
3 times 10 to the 19th.
No. Okay, guys, hold on a sec. We need to have some school in here, okay? Y'all punching wrong. Did anyone get it right?
I got
times 10 to the 7th.
Count better.
10 to the power of 6.
Count even better. All right, look, come on. You ready? I want to make sure you can see the problem and my thing. So 4.4 times 9.5 exp12 divided by 1.4 exp6.
Yep, I got that.
So would it be 3 times 10 to the 7th?
Oh, yeah.
Did I count that wrong
Yeah, I'm
too?
sorry. Geez. Someone said times 10 to the 7 and I criticized them. I'm sorry. That's my lack of sleep talking right there. Who had gotten to, I want to clarify this. Someone said 3 times 10 to the 7 and I criticized them. Who was that? Philemon, this is the second time I did that to you today, huh? All right. So, or I did this to someone else earlier. Philemon, yes, despite all those years and all those chemical trail of tears, you did do it right. You can feel proud of yourself. It's 3 times 10 to the 7 fake centimeters. And the way I would write that, honestly, because you know how I like to move decimals around, that's 30 million fake centimeters. I just slid the decimal place back 1. Guys, I don't know if you know what 30 million centimeters means, but 30 million centimeters would be 300 fake kilometers. In other words, the reason why they didn't ask you to do part A for stars is if you tried to make a scale model where the diameter of the sun was 1 centimeter, about this big, you would have needed to have a piece of paper the size of New England, and the nearest star, Alpha Centauri, would be another steel ball bearing located somewhere in northern Maine, okay? So the distances between stars are closer than galaxies, but relative to their diameters, galaxies have a 1 to 25 diameter to distance ratio, but stars have a 1 to 30 million diameter to distance ratio. So if we were rolling these marbles across, who's more likely to collide? 2 galaxies or 2 stars?
The galaxies?
Yeah. And here's something crazy. Because stars' diameters relatively are so much smaller than their distances, there are virtually no astronomy pictures of colliding stars. You never
Is
see
that
that.
why it's bigger? It's bigger. Is that why galaxies collide because they're bigger than stars and there's a bigger amount of space in between them?
Yes, or rather, their diameters are large enough where they bump into each other. And
Yeah.
I don't know if they understand what you're referring to, but we see cool examples of galaxy collisions all the time. One of my favorite astrophotos is of a set of colliding galaxies called Stephan's Quintet. And let me show you this picture. It's just really wild here. This is a picture of several spiral galaxies. Each of these contain trillions of stars. And check out this is seen probably in non-visible wavelength. Let's do this Hubble Space Telescope photo. Check out those 2 spiral galaxies. Yeah, right here. Those are 2 spiral galaxies. There's the bulge of one, there's the bulge of the other, and they're in the process of slamming into each other and mixing and merging all of their stars together. By the way, Milky Way is currently 2 to 3 million light years away from Andromeda, but the Andromeda galaxy and the Milky Way are on a collision course. And in roughly 5 to 10 billion years from now, the Milky Way galaxy and the Andromeda galaxy are going to smash together and all of their stars will mix. What's funny is because the stars are so small in diameter compared to the separations, when galaxies collide, the stars don't actually collide with each other, but it's almost like if you had 2 swarms of gnats that all kind of came together, like basically the galaxies will swirl together and all of the stars will kind of mix around, but none of the stars will actually hit each other. It's so wild and so cool. So this is an example of how using scale models and dimensional analysis, we can learn something really cool. Let's get that last point down. We have one last sentence to write, and I had a lot of buildup, so forgive me, I'm a bit theatrical. The last part of part B should go like this. However, the distance to diameter ratio for galaxies. Oh, let's try this. Well, 25 and 30 are about the same, so it's still a factor of 1,000,000. Let's do it this way. The distance to diameter ratio for galaxies is, or are, Jesus, where's my English here? Are millions of times smaller. I don't really like the way I said that. I should have said, you know what? I'm really unhappy with that. Let me fix this. The distance to diameter ratio for stars is millions of times greater than that of galaxies. So galaxies are much more likely to collide than stars. Sorry, my handwriting got kind of shit there. Can you guys see that? The distance to diameter ratio for stars is millions of times greater than that of galaxies. So galaxies are much more likely to collide than stars. That's an A. Whew. All right, not all the problems will be that gruesome, but that first one is a bit of a doozy. You'll discover, students, that sometimes I really like to take my time with a certain problem, and I like to lovingly caress it and really zoom in on it. And then other times I'm going to try to blast us through. So I'm going to try to do some blasting now so that we can eventually finish this damn project. Is everyone done copying? How you doing, Mariah? You're good? Anyone, Andrew?
I'm good.
Okay. Anyone need another second, or can I move? All right, I'm moving. Okay, we just killed chapter 142. Let's do chapter 149. Hey, Taryn, are you down to read a problem for me?
Let me just grab it.
Sure.
Oh, when we submit this, do we take a picture and post it on Blackboard, or are we just gonna type it into Blackboard?
Do not type it into Blackboard because I want to see the maths looking nice and neat. What you'll do is you'll take a photo of your pages, and then you probably should send it to your computer. You can upload it from your phone, but I think it ends up getting weird. You'll go to the homework section. You click this. Well, you'll click homework 1. Okay. And then you'll scroll to here, browse local files, and you'll upload your pictures there. You can upload a JPEG or a PDF. It's got to be something I can read. Okay. Make sure it shows up in the little preview box. And I
Okay,
covered
thank you.
this in our last section. Okay, Taryn, you good to go?
Yes, I found it.
Okay, what's the title?
It's called Universal Scale.
Okay, hit me.
Suppose we wanted to make a scale model of the local group of galaxies in which the Milky Way galaxy was the size of a marble, about 1 centimeter in diameter.
Basically, this sounds a lot like the last problem. They didn't explicitly say it, but we know from the last problem, Taryn, that the diameter of the Milky Way is about 100,000 light years, and we're setting that equal to a marble, about 1 centimeter, right? Take a moment to write that down if you want before continuing. All right, proceed when you're ready.
So it's a 3-part question. The first one is A, how far from the Milky Way galaxy would the Andromeda galaxy be on this scale?
Okay, how do we do this, Taryn?
Just give me 1 second. I'm trying to get the words out.
Sure.
We would want to use a scientific, not scientific notation. Dimensional analysis.
Yes, that's right. All right, so what are we trying to convert? How far away is Milky Way and Andromeda? How far apart are they?
They're pretty far apart.
Well, use the number from the last problem.
Okay.
Sure. Phone a friend. Someone else can contribute if you know.
I got it.
No, that's 4.4 light years is to Alpha Centauri. This is
okay.
Milky Way to Andromeda.
Okay. Oh, it's 100,000 light years, and the distance is.
Oh, yep. And the distance is.
2.5 times 10 to the 6 light year.
Good. So that's what we're supposed to be converting here, right? We know that the true distance is 2.5 million light years. And we want to know how far apart they'd be in fixed. Boy, this sounds really familiar, doesn't it? Doesn't this remind you of something that we did like 5 minutes ago? Anyways, let's do some dimensional analysis, Taryn. How do I do it?
All right. So you're going to start your problem with 2.5 times 10 to the 6 light year.
Good.
And then you are going to write down the number to convert with its units, and then you add multiply by a division bar for part 2. The first on the top is going to be centimeter
Prime, fake centimeter.
prime. And then on the bottom, it's going to be another light year unit to be able to be canceled out, and it's going to be 100,000.
And where do the numbers go, buddy?
One goes on the top, and then 100,000 goes on the bottom.
Good. So basically, this is a redoing of what we did in part A in our last problem. I assigned the problem knowing that we would repeat ourselves. That's okay. And what do we get for an answer then?
25 centimeters.
Good. Put a box around it, because that's our answer, and that's a classy move. Okay, Taryn, when you're done, read me part B.
Okay. Part B is, how far would the sun be from Alpha Centauri on this scale?
Philemon, how far away is Alpha Centauri from the sun?
4.4
4.4 what, inches?
light years.
Thank you. Okay. Philemon, what do you think we should do? By the way, Philemon, this is different than the last problem because we're still using the same scale model of 1 fake centimeter is equal to 100,000 light years. So we're doing this a little different now. How should I proceed, Philemon? Here's a hint, buddy. Dimensional analysis. Okay, Philemon, you and me are going to have a little play date here. So I want to work this one with Philemon because I want to train you guys. Philemon, can you flip open to that section of your notes that says the 4 steps of dimensional analysis?
So we got 4.4. I mean, write down the number of convert with its units.
With its units. So what would I write down?
4.4 light years.
Excellent. What's step 2?
Multiply by the division bar.
Good. All right. That's not too hard. I just did that. What's step 3?
Put the units in first.
Okay, that's your job. Tell me what goes on top and what goes on bottom.
Light years on the bottom.
Yep.
And
what are we converting into?
Centimeters?
Yep, fake centimeters. Scale model centimeters. All right, what's step 4?
Put the numbers in second using conversion factors.
All right, once again, that's a you job. So what goes on top and what goes on bottom?
1 on top.
Yep.
And 100,000 on the bottom.
Good. Okay, guys, punch them up. Punch them up and tell me what you get. Nice, Mateus. Let's see if these guys can catch up here. Oh, yeah. Nice. Cheyenne, how should I write that down? Brian, that looks good. I like your moves, Brian. Amy, I'm having trouble. It's a little dark. Can you? Walter, yes. Walter, good. Yes, Amy, good. Did someone have a question for me? How can I help?
No, it was just me saying how to write it down. I was going to.
Oh, yeah. Cheyenne, do that. That's what I want. How should I
it's 4.4 times 10 to the -5th power.
Good. And what are your units?
Light years.
Good. Nope. Bad.
Oh, no.
Look at your dimensional analysis. What's left over?
It's centimeters. It's centimeters. Yeah.
Yeah, because light years cancel out. Good. And the other thing you did good, Cheyenne, is I wanted to make sure that you were going to put the times 10 back in, okay? And you did that, so that's great. You have to write down the times 10. Put a box around it. That's a classy move. Okay, Taryn, what's part C?
All right, part C. How far would it be from the Milky Way galaxy to the most distant galaxies in the observable universe on this scale?
Okay, this is one of the reasons why you guys want to do the homework problems with me. If you were doing this on your own, this would probably be a stressful point in the question because most of you don't know how big the universe is or how far away the most distant galaxies are. Now, yes, they do include that information buried somewhere in chapter 1, but the likelihood of you having carefully read chapter 1 and remembering it is probably close to 0. So this is why it's nice to have me around. I can tell you that the universe is about 13.6 billion years old. So although the nearest galaxies will be a little closer than that, we could argue that 13.6 billion light years, that's about as far away as we can see into space because light hasn't had enough time to travel beyond that. This is what we call our observable universe. It doesn't actually matter how big the universe is. You can only see so far into it because it takes time for light to travel to you. So we're going to use 13.6 billion light years as a kind of radius of the edge of the universe. So let's start there with 13.6 billion light years. And then let's do our dimensional analysis. Cheyenne, what should I do for units here?
You should have centimeters on the top and light years on the bottom.
Good. And now give me the numbers.
It'd be 1 centimeter on top, and then the 100,000, right?
Yep. Okay, guys, punch them up. Brian, can you read that out to me, buddy? What'd you get?
I got 1,360,000.
Hey, can you punch that again? I think something happened. You're close, but you're off by a factor of 10, I think. I've already screwed up twice today, so let's see if I remember correctly. Yeah, that looks a little better, Cheyenne. Brian, I think you're off by a power of 10 somewhere, so punch it again.
Yeah, I got 136,000 this time.
That's good. And that's 136,000 light years. Centimeters. Put a box around it. That's a classy move. Okay, we're done the second problem.
Professor?
Yeah.
Why isn't that 1.36 times 10 to the 5th centimeters?
Good question. Philemon, because we have a rule in this class. Do you remember what the rule was for scientific notation?
Up to a million, right?
Right. And since 136,000, by the way, Philemon, you could have wrote that as 1.36 times 10 to the 5. It's not that that's wrong. It's just about what's in good taste and what's stylish. You know what I mean? Like if you were going to your wedding, most people don't wear blue jeans. I mean, you could. Why not be different? But most people think that there's a sort of formality to things. I like to think we bust out scientific notation when the number becomes too ugly to look at. But I'm okay with 136,000. You know what I'm saying?
Gotcha.
So that's why I did it like so. In the other case, though, when it comes to tiny numbers, even how do I put this? Even a big tiny number can still look ugly. So I like to go to scientific notation a little bit faster when it comes to tiny numbers. In any case, I hope you guys have that down. That's question number 2 down the hatch, or question 49. All right, moving right along. I need to erase this. Andrew, how are you doing?
I'm all set.
Anyone else?
I don't know what I did wrong on the calculator, but I also got 1,036,000, I think it was.
Let's show you. You're probably not using your EXP key correctly. That's what I suspect is happening. So why don't you watch me do it? Okay. We've got 13.6, And to do billion, I'm going to do EXP9. Just EXP9. And now we will divide by 100,000.
Okay.
Did it? All right. So you figured out what you did. Okay, awesome. Love it. That's actually really helpful for students who are watching the videos later. They don't get to ask the live questions, so that can help them too. So keep those questions coming. I'm going to erase this now. Tegan, since I was just talking to you, maybe you could read the next one for me.
Yes, hang on.
So this is chapter 2, number 53. Guys, I'm going to turn the temperature down in my apartment because I'm starting to like sweat. So just look that up for me and I'm going to be right back. 1 second. Okay, how we looking?
I got it. I just need to pull it up. Chapter 1. Chapter 2, question 53.
Yeah, what's the title? I like to hear the title.
Title is how do I pronounce that? Arc minutes and arc seconds.
Good. So this is some practice with those angles. Okay.
Okay. You want me to read the rest of the question?
Sure.
It says arc minutes and arc seconds, there are 360 degrees in a full circle. And part A says how many arc minutes are in a full circle.
Okay, let's stop there. So Tegan, since I'm talking to you, how should I do this? I think we should use a legendary technique known as fill in the blank. What's the technique called? Look in your notes.
Dimensional analysis.
Yeah, dimensional analysis. Okay, so how do we do that? Let's read the steps.
Sorry.
So at this point, Tegan, here's wait, Tegan, did you hide from me? Did you just go into troll mode? You can't hide from me. All right, you think you can hide from me? No way.
My mic was on. I'm still here. I just turned the camera on.
All right, okay, all right. That's
Camera
okay.
off. So I'm still here.
All right, cool. So Tegan, here's how we'll do this. You took some notes today, right?
No, I wasn't here for the first part of the class.
Oh shit. Okay. Well, no wonder you're confused. All right. Well, Tegan, you stay on standby here. Brian, do you have your 4 steps of dimensional analysis?
Yes, I do.
Okay. So why don't you walk me through this if you can, or let's walk through it together. What should I do, buddy? What do you think? And if you don't know what to do, let's just read the steps of dimensional analysis together.
Write down the numbers to convert with its units.
So what am I trying to convert here, Brian?
You trying to convert 360 degrees or?
Good. So let's write that down with its units. That's step 1. What's step 2, Brian?
You multiply by division bar.
Good. What's step 3, Brian?
Put the units in first to cancel.
Okay, so give me some units, Brian, top and bottom.
Arc seconds and then arc minutes on the bottom.
Hold on. In part A, Brian, they've asked how many arc minutes is that, right? So do you want to revise your answer?
Arc minutes on the bottom?
And what would go on top?
Arc seconds.
Okay, something about this I don't like. Let's do what's called.
I know.
What are you thinking, Andrew?
All right. So 360. So
No,
at
no,
the
no, no.
bottom, it.
No numbers. I don't want to hear about numbers. Numbers are boring.
All right. So
I'm talking units.
So the degree signal at the bottom, and then the.
Oh, okay.
What was it?
Degree signal and then the prime.
The what do you call it? The arc minute symbol on top.
Good. Now let's just slow down time for a second. Brian, I want to come back to you. Brian, the reason why, and you might have already figured this out, the reason why this won't work is we need the units up here to match the ones down here so that they cancel out. The way this happened, you wouldn't cancel out your units. So Andrew's suggestion
degrees on the bottom.
Yeah. Degrees are what we're trying to kill off. And we want arc minutes to come into existence. So we'll put arc minutes. Remember, the symbol for arc minute is a apostrophe at the top. Okay. Okay.
And
now.
arc seconds is 2.
Well, arc seconds we'll get to later. Let's make sure we remember why we did this. Let's cancel out our units. The degrees cancel out. Okay, Brian, what is step 4 of dimensional analysis?
You put the number in second using conversion factors.
All right, Brian. So from our notes today, we need a conversion factor from degrees to arc minutes. What is that conversion factor?
That is 60 arc minutes.
Is equal to?
Is equal to 1 degree.
Okay, so what number goes top and what number goes bottom?
So 60 goes on top and 1 goes on the bottom.
That's right, because there are 60 arc minutes in 1 degree. Okay, multiply them up and tell me what you get.
I got 21,600.
Nice.
Arc minutes.
Nice.
I did as well.
Nice. Put a box around it. That's a classy move. Okay. Was it Tegan? Were you our reader? Hey, by the way, Tegan, are you hiding from me now?
Hi.
Hi, Tegan. Tegan, I don't know if you noticed this, but the thing that happened earlier today when I taught people the 4 steps of dimensional analysis, that's like a wicked important part of this class.
Mm-hmm.
So you need to promise me that you're going to go back and put those notes into your notebook after this.
Yes, I am.
All right. I can't stress enough. Like, there are days where you can drift off, but although it's not very fun or exciting, the 4 steps of dimensional analysis are a tool that we need every single day. So make sure you go back and get that stuff. Okay.
Mm-hmm.
All right.
I will. Don't worry.
All right. I like it. Tegan, what's part B say?
Part B says. It says, how many arc seconds are in a full circle?
Okay, how many arc seconds? Tegan, even though you don't have the 4 steps, let's see if you and I can bash this out. We're looking to convert this now into arc seconds. What are we trying to convert into arc seconds? What's our starting number with its units?
360 degrees.
Good. So let's start there. So we write down the number that we want to convert with its units. Now, the second step is just to not think, just to make a division bar. The third step, Tegan, is to put units in. I need units on bottom and units on top. What do you think we should do?
Degrees should be on the bottom.
Absolutely. That's the only way they'll cancel out. And what should go on the top?
Seconds.
Arc seconds.
Arc seconds, yes.
Now, hold on. I want to slow down time for a second. I agree with you, Tegan, that we do want to convert degrees into arc seconds. And if you had a conversion from degrees into arc seconds, well, then that would be perfect. The problem is, Tegan, I don't know if you missed the entire lecture today, but I gave the class 2 conversion factors. I said 1 degree is equal to 60 arc minutes. And you might even want to write this down on your paper here. And I said
That's what I'm doing.
1 arc minute is 60 arc seconds. But Tegan, I did not give you a conversion from degrees to arc seconds, not yet anyways. So this won't work because you don't have a conversion factor. Do you see what I'm saying? We don't know how many arc seconds are in a degree right off the top of our heads, but we do know how many arc minutes are in a degree. Let's first convert to arc minutes. And what we're going to do, Tegan, is we're going to go back to step 2. We're going to make another division bar. And now tell me what units to put in. We've canceled out degrees. What units should you put in on the next division bar?
On the bottom will be arc minutes and on the top will be arc seconds.
Exactly. Okay, now that we've put all of our units in, and you'll notice that my arc minutes have canceled out. Now, Tegan, you've got one more job. I need you to put the numbers in last using the conversion factors. So use those 2 conversion factors and tell me what numbers to put top and bottom.
On the first division bar, on the top, you're going to put 60, or yeah. And then on the bottom, it's going to be 1.
That's right, because there are 60 arc minutes in 1 degree. And over here?
It's gonna be 21,600. Right?
No.
Oh wait, I'm looking at the bot. I'm trying to relate the problems.
Those are your conversion factors right there.
Okay. So it's gonna be. So it's gonna be 60 and then 1 at the bottom.
That's right, because there are 60 arc seconds in 1 arc minute. Excellent work. Okay. Now, guys, punch that up and tell me what you get. Zach, that's a little too small, bud. Something went funny there. Let me see. Cheyenne, that looks good. Brian, that looks good. Andrew, that looks good. Looks like some of you are getting it. So what should Taryn, I like it. I like your pink calculator styles. Yes, Mia, that's good. Yes, Walter. Yes, Mariah. Amy, how you doing? I haven't checked up on you lately.
I got something wrong.
Wait, say that again, Amy.
I said I got it wrong.
Okay, well, do you want to get it right with me?
Yeah.
Okay, so let's do it together. Ready? Punch with me. Yes, Zach, that's much better. We'll keep all our sig figs though here. So 360 times 60 times 60. That's what I got. Now, Zach did a cool thing. Zach's a troll in the background who chatted 1.3 times 10 to the 6. I'm okay with that, but here I'm going to let you guys keep all of your precision. This is a level 2 discussion that not everyone's going to follow, but I'll give it a shot. How many sig figs can I keep here? I can actually keep all of them, because in these conversion factors, these are not measurements, but we precisely define exactly 60 arc minutes in 1 degree, and we precisely define exactly 60 arc seconds in 1 arc minute. That means those conversion factors have infinite precision because they're conceptual. They're not a measurement, okay? So Zach, try again, or anyone else who wants to. What should I write keeping all my sig figs? And by the way, Philemon, the number's bigger than 1,000,000, so yes, we need scientific notation.
Is it 1.29 times 10 to the 6th?
I'm going to keep all the digits. 1.296 times 10 to the 6. And what are my units?
2 little bar thingies.
Yeah, be careful. Don't make it look like 611, okay? Honestly, if Zach had put down 1.3 times 10 to the 6 arc seconds, I'd probably accept that. But since I'm here talking to you anyways, I want the more advanced students who are with me to understand that you can keep all of those digits of precision, because these are not measurements. They are perfect conversion factors, conceptual ones. A similar analogy would be, if you ever took geometry class, you will have learned that the radius of a circle is half of its diameter. The half does not have a measurement associated with it. The radius is exactly half of your diameter. It's conceptual. That's an analogy. Okay, who was our reader? I've already lost track of who the bloody reader was. I'm so sleep deprived. Was that Tegan?
Yeah, it was me.
Tegan, why don't you hit me with part C?
Okay. Part C, it says the moon's angular size is about a half a degree.
Mm-hmm.
And it says, what is this in arc minutes in arc seconds?
All right, so we got two mini problems. Hey, Amy. Amy, you've piqued my interest. I want to get to know you, okay? Amy, I think you should help me convert 0.5 degrees into arc minutes. Want to try it?
I'll try.
Why not? Can't hurt to try. Let's use our steps of dimensional analysis. Do you have those notes down?
I wasn't here earlier.
Oh, so that's probably part of the confusion. You guys can see what happens when we miss the lectures. The lectures actually turn out to be kind of important for training. Now, I'm sure many of you couldn't be here because you might have had other obligations. But Amy, I want to give you the same spiel I gave Tegan. You promise you'll go back and carefully watch that video and take all the notes?
Yeah.
Okay, cool. But Amy, now that we're here hanging out, that doesn't mean we can't learn. It's still time to learn. So I'll just guide you a little bit more, okay? So Amy, we start off by writing down the number to convert with its units, and I've already done that for you, 0.5 degrees. And the second step is to put in our division bar. So I'll do that. Okay, Amy, now it's your turn to shine. We want to convert from degrees to arc minutes, and we have to put the units in first, the numbers in second. So Amy, you're going to give me the units. What units do I want on top, and what units do I want on bottom? Want to take a guess?
You want the arc minutes in the top and then the degree in the bottom.
Excellent. I concur. And that means the degrees will cancel. Okay. Now the last step is to put the numbers in using those conversion factors. So what should I put in, Amy?
60 in the top and then 1 in the bottom, I mean.
Excellent. Okay, and that means 0.5 times 60. You can do that on your calculator or do it in your head, whatever is easier.
It should be 30.
Yeah, half of 60 is 30 arc minutes. Okay. Let's go ahead, Amy, and we'll just drive that point home. Now we've got 30 arc minutes, and we want to convert that into arc seconds. The first step is to write down what you want to convert with its units. And then the second step is to make a division bar. Amy, this time, what units should I put top and bottom?
You want to put arc seconds in the top and then arc minutes in the bottom.
Good. And what's your conversion factor?
60 and 1.
Okay. And multiply them up, and what do you get? Sometimes these homeworks can take up, oh, fuck. Yeah, we're going slow today, but we got to get this done. We can't stop until we're done.
1800.
1800. And what are the units?
Arc seconds.
Okay. Before we go on to do the last two problems, let me say something. Traditionally, when I run office hour sessions, especially live, they always take 2 hours. But as time has gone on, I've gotten really good at streamlining most of the homeworks and getting it done somewhere between an hour and an a half. So since the times were arbitrary, I try to schedule an hour and a half. But honestly, I knew this homework was going to really suck because you guys are just really new to the class and you don't know the style or how we do things yet. So everything's taking a lot longer than normal. In general, the homeworks won't go this long, but this is your first homework and we have to do it right. So this is what's going on here. Keep in mind that I can go faster, but you guys will start to get lost. That's okay, Mia, but Mia, if you have to go to work, you have to promise you're going to come back and do these two problems. So I give you a 25 out of 25, right? Where is Mia? Oh, hi, Mia. Okay. So Mia, You can even watch the old videos where we do these last two problems, or you can watch the new one when I post it today. But when you get out of work, no matter how tired you are, or you have until Saturday, get those last two in for me, okay?
I will. I'll do it tonight.
Awesome. You're the best. Good luck at work, buddy. Okay, let's crank out these final two problems. Has everyone got this? I'm going to erase.
I still have to write it.
Oh, sure. Let me know when you're done, Cheyenne. I think that was you. I am not doing my hashtag best here. Cheyenne, you good?
I'm all set.
All
It
right,
wasn't me who said it was someone else.
Oh,
yeah,
I'm
it was
sorry.
me.
Wait, who's me? I'm losing track of everyone here.
Me.
Oh, hi, Kiana. Kiana, are you good?
Yes, I finished it.
Awesome. All right, I'm erasing. Okay, Kiana, since I just heard your voice, what do you say about reading me chapter 2, number 55?
Yeah, let me just open it up.
Okay. I like the titles too. So Taryn, did you buy that calculator to match your pink lights, or was it just coincidence?
Just a coincidence.
Pretty cool. I dig it.
Okay, I think I got it now.
All right.
We're on 54, correct?
55, I think.
55.
What's the title?
Are we?
Yeah, it's 55.
Okay.
It is 55. Oh, I wrote the wrong number down on the other one. All right, my bad. Okay, so it's angular conversions 1, and the following angles are given in degrees and fractions of degrees. Rewrite them in degrees. What does it say? Arc minutes and arc seconds.
Beautiful. I want to give you guys a little background as to what's going on here. If you have some random degree, like let's say you've got 29.654729 degrees, that can be expressed in degrees, arc minutes, and arc seconds. Now, you guys probably don't understand what they're asking, but when you list the coordinates of a star, there's kind of a classy way to do that, and I'd like to just show this to you. Let's go to the Wikipedia page for Betelgeuse. Not the movie, but the star. Hopefully that takes precedent, but who knows? Okay. I want you guys to just quickly look on this Wikipedia page to see the coordinates of Betelgeuse. In fact, I might kind of zoom in on this. I want you to check out how they, where are we here? I want you guys to look at the format. Look at the format, for instance, for declination. The classic format is to list a whole number of degrees. So Betelgeuse is +7 degrees on the sky, and then a whole number of arc minutes, 24 arc minutes, and then a whole number or possibly a fractional number of arc seconds. So we would say the coordinates of Betelgeuse are 7 degrees, 24 arc minutes, 25 arc seconds. That's the sort of thing that they're trying to get you to do here. And that probably wouldn't have made sense to you guys without some explanation from me. And that's how I can be useful to you. So let's try this first one nice and slow together. Kiana, what's part A ask for us?
All right, let me check. It just, for 55, it just has options for numbers. It's not really questions, it's just like A, B, C, D, or E.
Yeah, and A is our first assignment.
Oh,
here.
duh. Hello. I'm
That's
sorry.
okay. That's okay. That's okay. We're all new to this game. So what's the number they gave us for part A?
24.3 degrees.
Okay, cool. Now, let's think about the format that we're trying to get this into. We're trying to get this into a format where we have a whole number of degrees, a whole number of arc minutes, and possibly a whole number of arc seconds. In a way, we already know what the answer to the whole number of degrees is, right? It's 24 degrees. So we've got that part down. How should we figure out what the arc minutes and arc seconds are? Does anyone know what to do here without me telling you? What do you guys think we should do?
Dimensional analysis.
On what? I agree, Philemon, but dimensional analysis on what?
Allow someone else.
Oh, sorry. Who said that?
That was me, Brian.
Oh, Brian. I'm sorry, Brian, because your hoodie's down. I can't. I'm still learning the voices here, and I didn't notice you speaking. Brian, yes. We want to do dimensional analysis, and Brian, I want you to do it. But what do you want to do dimensional analysis on?
24.3.
Well, we've already got the 24, right? We know that there's 24 whole degrees. So what we actually need to do dimensional analysis on is
arc minutes.
Sorry?
Yeah, arc minutes and then arc seconds.
Well, we want arc minutes, but what are we trying to get into arc minutes? Does anyone follow what's happening here? This might be a little confusing.
Arc seconds.
Well, that's going to come later.
Degrees?
Right, but how many degrees are we trying to convert?
24.
No, we already have the 24 as a whole number of degrees. The issue isn't the 24. The issue is...
Is it 24.3?
No.
Are we supposed to subtract 24 from 360?
Not from 360. We're trying to convert this into a whole number of degrees, arc minutes, and arc seconds. By the way, you're... Yeah?
2 times pi divided by 360?
No.
No, you just times 60 for each one. So
Wait,
you times 60 from the degree to the minute, arc minute.
No, it's too vague. This is why we have the 4 steps of dimensional analysis. What is the first step in dimensional analysis?
Oh, I get you.
Write down the number to convert with.
Down the number to convert.
Right. Your problem right
With
now
its
is you don't know what you're trying to convert. Your problem is step 1. Hey, Mateus, what's that kitty's name? I remember that guy.
Piglet is his name.
Oh.
He's a pretty big cat. Okay, maybe you guys need my help here. The issue isn't the 24. The issue is the freaking 0.3. It's the 0.3 that's
Oh, I
a
should have
fraction of a
said
degree.
that.
And that's, so someone said 24.3, but it's, and then they said subtract 24 from 360. You guys were all over the place. What you want to convert using dimensional analysis is the fraction of a degree into arc minutes. So Brian, how should I do that?
So we're trying to get arc minutes, right?
But why, says Zach. Okay, Zach, I want to answer that question. It's customary, like if you're in the military or if you're doing geocaching or anytime navigation is used, it's customary to express your position rather than saying your latitude is 42.96197 degrees. It's like time. For the same reason we break hours into minutes and seconds, because it's easier for the mind to remember. Imagine if I said this class will start at 11.8762 hours. That would be some fucky wucky shit that would mess with your brain, right? But if I say, hey, this class is going to start at 8 hours or at 11 hours and 50 minutes, you're subdividing it into whole numbers that are easier for the mind to remember. So rather than expressing 24.3 degrees, I want to know 24 degrees, this many arc minutes, and this many arc seconds. We know how many degrees. We have to figure out how many arc minutes are represented by this fraction of a degree. So someone tell me what to do.
Oh, I got you. All right, I got you with the units and the numbers. So at
Andy,
the bottom, degrees, and then at the top it's arc minutes.
excellent, Andrew. And now
And then you're canceling out the degrees. And then it's gonna be 1 degree and 60 arc minutes.
so where does the 1 and the 60 go?
The 1 goes at the bottom and the 60 goes on top.
All right, what does that give us if you multiply those two?
18.
And notice that's a nice
18 arc minutes.
18 arc minutes. So let's put in the 18 here. And that means how many arcs? Let's see if Zach follows me. Zach, how many arc seconds do I have? This could potentially be a confusing question. So what should I put in for my arc seconds, people? I follow you, Zach. Yeah,
Do we
I have to.
convert that?
No, 18 is the arc minutes, right? So what goes here then?
But you don't convert that to get the. Oh wait, hold on.
Isn't
No,
I need
no.
us to give you what the arc seconds is.
Pardon?
Oh, you're asking us what
Yeah.
the
I wanna
arc
know what the-
seconds is? It's 1080, right?
No. It's 0 because this is exactly 18 arc minutes. There's no fraction of an arc minute. I think as we go forward, you guys will start to get it. This number can be expressed as 24 degrees, 18 arc minutes, and 0 arc seconds.
Why'd you put 2 zeros?
That's something called cell padding. I've discovered that when you're taking data and you're writing it down, it's really nice to keep a consistent number of digits. It's good to keep you from making errors like clerical errors, and it's very good in computer science to have the same number of digits no matter what you're doing. So that's a cool question you just asked there. I did that. There's a madness to my methods. I want to keep the same number of digits for each box, like I was entering it into a computer system. Okay.
Makes sense.
Now, what's B?
B is 1.59 degrees.
All right, let's see if we can speed this up. So what do I put in the first box?
1.
The 1.
A 1. We'll cell pad that. Okay, now we got to figure out our arc minutes. How are we going to do that?
Our arc minutes. Oh wait, we already did it. It's 18, right?
No, that was A. We're on B now.
All right, so you have to convert that.
Convert what? What's that?
The 18.
Nope.
0.59 times 60.
Oh yeah, the 0.5. Yeah.
0.59 degrees. Let's do dimensional analysis, people. Let's not get cocky here. Units?
60.
No. Units.
Oh. Yeah, degrees on the bottom.
What about on top?
Arc minutes.
Okay. Now you can put your numbies in. Work with me, people. I need a big
Oh,
one.
I got it. Should be 60 on top and then 1 at the bottom.
All right, punch them up. What do you get?
35.4
Units?
arc minutes.
Good. So what do I put in my next box then?
35.
Excellent, Kiana. You're with me. All right, Kiana, now we got to get the arc seconds. What do you think we should do?
It's Cheyenne talking.
Oh, I'm sorry. Jeez, I wasn't even looking. I thought I knew who it was. Cheyenne, I am so sorry. You know, guys, I had really bad insomnia last night. So it's amazing that I've even been this coherent. I am not doing my hashtag best. I can't believe I've made it this far. So Cheyenne, deepest apologies. You seem to be with me. So tell me what to do now.
So what's left over is the 0.4 arc minutes.
Good.
So you do that times the division bar with 60, or excuse me, the arc seconds on top, arc minute on the bottom.
I like your style, kid.
So, and then so it'd be 60 over 1, and then you would solve from there, which would be
6 times 4 is 24, right?
yeah, be exactly
Yeah.
24.
That 0 cancels out that point, so it's 24 arc seconds, and that's what goes in the last box. Awesome. Hey, Cheyenne, you're with me. This is good. The rest of you are going to be catching on too, but it takes a minute to figure this out. Okay, so who is I lost track of who the reader was because my mind is mush. I got a mush.
I
brain.
was.
Okay, could you read part C for me?
Sure thing. This one is 0.1 degrees.
Okay. So
The
part
next two are pretty similar to that.
Yes. Well, that's good. That means we can do it quickly. Okay, so how should I begin? What's in my box?
The 0?
0 for degrees because we're less than 1 degree. I'm going to use cell padding and 00 that for consistency. Now what do I do?
Use the method
Use the
that I
method.
keep forgetting the name of.
Dimensional analysis.
Dimensional analysis.
Yes, that. I keep forgetting the name of it.
All right, let's do it.
All right, I got
I'm
it.
gonna do the Donald
So
Trump dance. You guys see that? Do 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 do. All right.
all right, so I got it. So it'd be the 0.1
Yep, degrees.
degrees, and then you're gonna times it by oh yeah, we gotta put in those units.
Yes, Andrew. Let's get some units in.
So 360 at the bottom.
No. Units.
Oh, units. Oh, degrees at the bottom, and then it's the arc seconds.
We go to arc minutes first.
Oh yeah, the arc minutes.
All right, what's my conversion factor?
Should be 360.
Nope.
Or no, wait. No, it'd be 1 over. It'd be 1 and then 60. So 1 at the bottom and then 60 up top.
Good. What's 6 times 1?
6.
60.
That means 06 arc minutes. And how many arc seconds?
0.
Good. Now you're with me. All right, bang. Let's do the next one. Let's do part D.
All right, let me go over. And D is 0.01 degrees.
All right, tell me what to do.
Put the 0 in the degrees box.
Like? Me likey? Now what?
Now the analysis.
Sure. Let's line them up. Line them up
So-
and bring it back. I sure did that last night. Okay, what are we doing here?
I think because I'm still trying to like get the whole thing down. I think it would be 0 degrees times and then
not
the
0
divide
degrees.
bar.
You're trying to convert the fraction of a degree into arc minutes.
Oh, so then it would be 0.01 degrees.
All right. Times division bar. Give me some units. This is Kiana that I'm talking to now, right?
Yes.
All right. Give me the units.
The degrees at the bottom and then the arc minute at the top.
Excellent. Okay, now give me your conversion factor.
60 and 1, 60 being on the top and 1 at the bottom.
Can you do that in your head? What's 6 times 1?
6.
Now you've got 1 0 here, but you've got 10 to the minus 2 there. So what should that come out to be? Punch it into your calculator, it doesn't matter.
Oh my God.
No, you can do it.
I don't have the calculator yet, and I'm like super bad at math. So like
No,
someone
no,
else might have
wait,
to do
where
this
are
part for me.
Hey, Kiana, if you don't have the calculator, then you have to do this the right way. Okay, You know that 6 times 1 is 6, right?
Yeah.
Here you've got 10, but here you have like 100th. So you've got 1 0 there, but you're minus 2 zeros there. So what do you think the answer is going to come out to be?
Oh God.
Not 6, but
oh Jesus. 60? Oh God, I feel dumb.
is anyone following me here?
It's 0.6.
Yeah.
Thank you. I'm so bad at math.
That's okay. You know what? That's okay if you're bad at math, because I'm the guy that you have to meet. I'm the guy that you have to interface with.
Yeah.
And I'm going to make you good. I'm going to make you good at math. That's my job. All right. 0.6 arc minutes. So what should I put in the second box? I want to see if you guys are understanding this.
It's in 0.
It's still 0. Good. All right. Now what do I do? Because we don't have a whole arc minute. We have less than an arc minute.
Calculate the arc seconds.
Okay. Help me do that.
You would put, would it be 0.6 times
arc minutes, please.
Arc minutes. Oh.
Always units. Always with the units.
Yes, 0.6 arc times 60 arc seconds.
I prefer you do the units first. That's a
Oh, arc seconds times arc seconds on the top, and on the bottom arc minutes.
Good. And now you can give me those numbers, Tegan.
It would be 60 over 1.
Okay. What's 6 times 6?
36.
36.
Right. Here you have a 10th. There you have an extra 0. They cancel out. 36 arc seconds. And we got one left to do, and then we have one problem left. Whew. Okay, what's D?
E is oh, we just did D. I think it's E now.
Oh yeah, sorry. Right.
No, it's okay. This one is 0.001 degrees.
All right. So I bet we could fill in these 2 boxes right away. I mean, I was hoping we could, but maybe no.
Both the degree and the arc minute are going to be 0.
Yeah, because we have even less than we did before, right? So 0, 0. In fact, that gets me thinking, who just said that? Who was talking to me?
Cheyenne.
I'm
Can you
sorry.
hear me?
I can
It's
hear you.
Cheyenne.
Oh, Cheyenne, right. So Cheyenne, what do you say that you and I just get right to arc seconds with our fraction, okay? So we'll start off with 0.001 degrees, and let's set up 2 division bars.
Okay. So for the first division bar, the top bar will be the arc minute, the bottom will be the degree, and for the second bar will be arc seconds, the bottom one will be arc minutes.
I like
so the
your
degrees
style.
both cancel out and both arc minutes cancel out.
I like your style.
So on the first bar, it'd be 60 over 1, and then the second bar the same was 60 over 1.
Okay. So let's see if we can do this. Hey, you want to be a real badass, Cheyenne? Let's do this in our head. What is 6 times 6 equal to?
36.
Now add 2 zeros and you get?
3,600.
Now take away 3 zeros because you've got 0.001. So slide the decimal point back. You have 3,600, slide the decimal back 3 decimal places, and you end up with?
Okay. 3.6.
Nice. That's rockstar style. And that's arc seconds, and we can leave this as a fraction. Nicely done in your head, too. I'm impressed.
Oh, so I just want to make sure if it's like not a whole number, it could be in fraction form for arc seconds, but it cannot be in for arc minutes.
And the reason I knew that, Cheyenne, is just because I'm now an old dog who's been looking at astronomy stuff for a while. And I remember, for instance, if you look at the angle here for the declination of Betelgeuse, you'll see they follow the same format. 7 degrees, 24 arc minutes, 25.4304 arc seconds. It's just custom. It's like tradition. There's no logic to it. This problem is just kind of indoctrinating you in the wacky astronomy lore, okay? Okay, thank God we've got one less to go. It's not too bad. We're almost done, guys. Keep the faith. We're getting through this. By the way, this will go faster in the future, but you guys are going to take a little while to adapt to my style and learning the things I want. Mateus will be able to tell you that as the semester goes on, we catch our groove and we can do this a little bit quicker, okay? And Andrew can attest to it as well. So, all right, let's get to who haven't I heard from here? Who wants to read? Anyone? Who's got that stuff? Walter. Hey, Walter, I haven't heard your voice today. Are you down to read me a problem?
Yeah, of course.
Thank you, sir. So let's read out chapter 2, number 58.
All right. Betelgeuse diameter. Estimate the diameter
One
of
second, buddy. Just let me catch up to you. One moment. Sorry. 58,
yeah, number.
title is Betelgeuse
Betelgeuse diameter.
Okay. Hit me.
All right. Estimate the diameter of the supergiant star Betelgeuse from its angular diameter of 0.05 arcsecond and distance of about 600 light years. Compare your answer to the size of our sun and the Earth's sun distance.
Okay, after we get the answer, we're going to compare it to the sun, whose diameter is 1.4 million kilometers. And we're also going to compare it to the Earth-Sun distance, 180, 150 million kilometers. These are what I call the givens. The givens are the required data. I'm actually doing you an extra solid by showing you what the variables are. They've given us the angular size and they've given us the distance. I think we should draw a picture to go along with this. Drawing a picture is actually wicked important. So let's draw our star. And that's its diameter. And we are looking at it from some distance away on Earth. This is our eyeball. We know that the distance is 600 light years. And we know that the angular size is 0.05 arcseconds. The goal is to find this quantity, the Betelgeuse diameter. This sounds like a job for what classic formula that we learned today?
Small angle formula?
Yes, exactly. And the small angle formula goes like this. S equals theta times d times 2 pi over 360 degrees. Write all that down. How should we proceed, students?
Fill in the blanks.
It's not quite that simple, actually. There's a little trick to this.
Dimensional analysis?
No. By looking at this, you could just put 0.5 for theta. Oh, you can't do that?
Nope. Why not? There's a whole trick to this problem, and I want to see if you guys can figure it out.
Is it dimensional analysis?
Well, eventually, yeah, that's coming. But first, we have to understand why. Why can't I put 0.05 arcseconds in there?
Because in the formula, it has 360 degrees.
Yeah. One of the requirements for this formula was the angular size had to be in degrees. But you've got it in arcseconds. So what the heck are we going to do about that, Mateus?
Dimensional analysis.
Okay, set them up for me, buddy. Tell me, show them how it's done.
Okay, so we are looking for the degrees. So we are going to start with what we have, right? Which
Yep,
is
what we have.
the arc minutes. arc seconds,
All right, so tell me what to write down.
which is 0.05 arc seconds.
Okay. Now what?
And then you're going to do the dividing. I forgot, what is the proper name for it?
Division bar?
Division bar, yes, that's it. And you're going to put arc seconds in the bottom and arc minutes on top.
Okay.
And then you're going to do 1 on top and 60 in the bottom.
Okay, that gets us to arc minutes, buddy.
And then we're going to do another division bar so we can get to the angles. And it's going to be degrees in the bottom. Yeah, degrees on top and arc minutes in the bottom.
Good. That way the arc minutes cancel out. And then the numbers?
And then it's going to be 1 on top and 60 in the bottom.
Okay, punch that up, guys. Tell me what you get. Here we would take, Amy, we had some issues with this before. We're going to divide here. We're going to do 0.05, divide by 60, and then divide by 60 again. What do you got?
1.4 times 10 to the negative 5.
Units?
Degrees.
Don't make that look like negative 50. Make it look like 10 to the minus 5 degrees. Cool. What about the distance? If I plug in 600 light years for distance, then I will get the diameter of the star in light years. Do you guys think light years are a good unit to measure the diameter of a star with? You and me both, Taryn. Can I measure the diameter of a star in light years? I mean, I could, but like, what if you were an entomologist and you tried to measure the length of an ant in meters? You'd be kind of like a whack job if you did that, right? Because an ant would be like 0.003 meters. That would be awkward. A more appropriate unit to measure the length of an ant might be millimeters. What's an appropriate unit to measure the diameter of a star?
AU or I can't pronounce it.
No,
Astronomical unit.
You know, normally, in this case, you end up turning out to be right. But normally, AUs are not a good unit for measuring the diameter of stars. It's just going to turn out that one of the weird things about the answer to this question. Okay, sorry, Philemon. We're almost done, too, but I feel you, brother. Just catch up on this last bit later, okay? All right, sorry it took so long. We'll work on that. We'll work on being faster.
All right, kids.
All right, let me speed this up because I can see that this is going to be an issue. I think kilometers would be better. So let's go ahead and convert to kilometers, okay? So 600 light years. I'll do this one for you in the interest of time. Light years on the bottom, kilometers on top. 1 light year is 9.5 trillion kilometers. Can you guys punch that up for me?
$5.7 times 10 to the 15th.
Units?
Kilometers.
Okay, I'm going to erase up top and we're going to set the problem up and plug all this stuff in, okay? Okay, so I have S equals, first I'll plug in the angle in degrees, 1.4 times 10 to the minus 5 degrees, times the distance in kilometers, 5.7 times 10 to the 15 kilometers, times 2 times pi over 360 degrees. Now, I'm guessing this is going to stress some people out punching that in. So do you guys want me to lead you through it? And you'll follow along?
Yes, please.
Okay. Make sure you're punching, though, okay? I want you to watch me do this. 1.4 exp -5 times 5.7 exp 15 times 2. Now pi is right above exp, so watch this. Times exp for pi divided by 360, and then equals. Did you guys get that? Hold up your calculator and show me that you got that. Yes, Mariah, you're cool. Yes, Walter. Yes, Andrew. Yes, Mateus. How about Taryn, Amy? I want to see it. Hold it up. Show me you got what it takes. Brian, it's a little hard.
I think I did something wrong.
I have what you have, but it's just because of the glare.
Yeah,
I
I feel.
turn on my light just so it stays on because it likes to shut off by itself.
Yeah, because it was good. All right, Brian, I trust you. Who said they were having trouble? Someone was talking to me there.
Cheyenne, I'm putting everything back in again to see if I.
All right, punch it one more time, and I can do this again. Whew. Amy, are you struggling?
I don't know what I'm doing wrong.
Okay, can we try this again? Try to keep up with me now because I'm fast, all right? All right, ready? 1.4 exp -5 times 5.7 exp 15 times 2 times pi divide by 360 equals.
Okay, I got it.
Yeah, okay. So how should I round this? And obvious this needs to be in scientific notation, right? So what should I write for my answer? Tell me what to write.
Should be 14 times
Nope.
10.
Let's do proper form, 1.4.
Or 1.4 times 10 to the.
To the what?
I'm saying 10
Ninth power?
to the 9th.
Ninth power.
Yeah.
What are the units?
Kilometers.
Right. 1.4 billion kilometers. Put a box around it. That's our answer. Okay. Believe it or not, guys, up to now, you've only gotten 4 out of your 5 points. Remember that one of the things we had to do is compare. And compare means something very particular in this class. I'm going to erase down here. From now on, class, when they say compare, they don't want to know, is this bigger or smaller than that number? Compare means to take the ratio to find out how many times bigger or smaller. Let's write that down. Compare in science means you take the ratio. Sometimes you can divide the big number by the small number. Sometimes you divide the small number by the big number. It's a question of taste. You will learn in time how to do it. For now, let me set up how this is going to look. We're going to divide the diameter of Betelgeuse by the diameter of the sun. We've calculated the diameter of Betelgeuse as 1.4 billion kilometers. In the book, they give us the diameter of the sun as 1.4 million kilometers. Divide them up. Or alternatively, we could ask, who's good at this? I had a good time with Cheyenne. Cheyenne, you're a hot shot.
Yes.
Cancel out the 1.4s. You know how this works. You subtract the powers. What's 9 minus 6?
3, yes.
So what do I have?
So it'd be so you cancel out the 1, yes, and then you have the 0.4. So would it be
The 1.4 is canceled. Okay, Brian.
Yeah, those are canceled. I'm just getting a little stuck now.
All right, just plug it into your
So it'd
calculator.
be
I was trying to be cute, but just plug it in.
sorry.
Geez, guys, I'm going to grow old and die here.
Betelgeuse is 1,000 times bigger than the sun.
Yeah. Yeah, my only point was 9 minus 6 is 10 to the 3. That's right, Zach. So it's 1,000. 1,000 times bigger than the sun. Okay, let's do our next comparison. We will now compare the size of Betelgeuse to the size of 1 AU. On the top, we have 1.4 billion kilometers. On the bottom, we have 150 million kilometers. Divide them up. What do you get? Hit me, Mateus.
9.33333.
All right, we'll forget about all those threes. How about 9? What's the meaning of 9? The 0.3s are boring. They're not interesting.
It's 9 times bigger than 1 AU.
Yeah.
Than the distance from the Earth to the sun.
Right, but hold on, Mateus, think about that. If Betelgeuse is 9 times bigger than 1 AU, right? Think about what that means for like Betelgeuse versus our solar system, right? Like, let me show you that slide from the beginning of class today. Function F5. So this star right there, this red star, if you put that into our solar system, sorry, my slides are a little clunky here. If Betelgeuse is 9 astronomical units, Betelgeuse, if you put it into our solar system, would basically swallow up Mercury, Venus, Earth, Mars, Jupiter, and barely extend out to the orbit of Saturn. That's how big Betelgeuse would be if you plopped Betelgeuse into our solar system. Oops. Betelgeuse would basically
That's pretty
be
crazy to think about.
right. That's one star. It's almost like the size of an entire solar system. That's why Betelgeuse is such a cool star, because it's just one of the largest stars we know about out there. It's an upper limit to how big and fat stars can be. It's totally wild.
Why did they name it Betelgeuse?
Pardon?
Why did they even name it Betelgeuse?
A lot of the names, there's a really cool answer to that, Kiana. People have been studying astronomy as far back as earliest civilizations. Think like Babylonians and Mesopotamians and Egyptians. During the Middle Ages, when Western Europe were busy burning each other at the stake and gouging out each other's eyeballs and poking each other's with fiery crosses, algebra and astronomy was preserved by Arabic astronomers. Many of the names of stars have Arabic origins. And for that reason, they'll have names like Aldebaran or Betelgeuse probably has some kind of an Arabic connotation. Now, over time, I've picked up some of the names of them, like in the constellation Cygnus, the star Alberio is Arabic for the beak. Now, I don't remember what the etymology of Betelgeuse is, but it probably means the shoulder in some ancient Arabic dialect. So there is a cool answer to that question. Those names go back thousands and thousands of years. Astronomy is a very old science. Okay, guys, I know that was a lot. It was certainly a lot for me because I was dead dog tired, but we did it, and I'm so proud of you for staying the course. I am going to do my best to make these homework sessions faster. That will depend upon you guys a little bit because I can only go as fast as you can handle it. But I think the first time was a learning exercise. Now listen, Taryn's getting her papers out. She's going to photograph them and she's going to upload them. Cool shirt, by the way. I like that. This is awesome. Very 80s. I'm into 80s like synth music and stuff. So guys, do you know what to do? Do you know how to submit these? Can I trust you to do that? All right, you're going to take the photo either from your phone and from your computer. You're going to upload it to that thing that I showed you earlier, right? And just for the benefit of anyone who forgot, you're going to go to Blackboard, excuse me. You're going to click homework 1. So you'll click over here in the homework tab. Then you're going to click on homework assignment 1. And if you scroll down to this button, browse local files, it will let you upload wherever your scans or your pictures are, okay? You can hit me up if you have trouble with that, but it should be obvious. Had a great time with you guys. I'm going to see you on Tuesday, correct? Andrew, did you get a haircut? Looking sharp, buddy. Okay, so I'll see you guys next Tuesday, okay? Have a great weekend.
You too.
Get those calculators. Take care.